Hi, everyone. Hey, Patrick. Hey, Viviana. Hey, Jake. Good to see you all.
Hello.
Hey, Antonio. It's good to see you.
Hello. I assume you want me muted still, right?
Meow.
Yes, now my cat has debuted on the live stream.
Nice. My dog has his yesterday.
Just so you know, we are live on YouTube and Zoom.
Yep.
So now you have famous pets.
Yep. With that, I'm going to mute and turn off video again. See you later.
Hello, everyone. Welcome to the 5th and last day of the conference. We really hope you've enjoyed it so far, but we're still not done. Today, we're going to have 2 more invited review talks, and then we'll have the second discussions of the conference. And with that, I'll leave the floor to Viviana Guzman, who's going to be the chair for today. Viviana, all yours.
Thank you, Alvaro. Welcome, everyone, to the last day of this wonderful conference. So I'm Viviana Guzman from PUC in Chile. And I first wanted to thank and congratulate, actually, all of the organizers for making all this wonderful conference, in particular, Alvaro and Enrique, who I know have been working so hard all this week and for many, many weeks. So thank you, guys. So today, the first talk is going to be from Patrick Sheehan from Northwestern University about the youngest disks, the class 0 and class 1. So Patrick, please go ahead and share your slides.
All right. Oops. Oops, sorry. I was just telling Alvaro and Enrique that even after doing this for 7 months, I'm somehow still terrible at Zoom. So give me a sec. Is everyone able to see my screen?
Yes.
Perfect. All right. Before I get started, I want to also echo what Viviana said, to just thank all the organizers for this conference, and particularly Alvaro and Enrique. I know from experience, and I'm sure many of us out there also do, how difficult it has been to pivot everything to a virtual format in the last few months. So I just want to say thank you to them for all the hard work they've put in to make this happen. Even though we couldn't all meet down in Chile, I've been really thrilled to see how many people have been attending and see all these really great talks contributed and invited, and all the discussion on Slack. And so on that note, I also want to thank everyone that contributed talks, and I hope everyone will continue to check the Slack for a few weeks after this, because I've definitely got a backlog of talks that I still want to check out. So hopefully you won't mind if I continue to pepper you all with some questions a little bit after the official end of the conference. So yeah, my job today is to talk to you about class 0 and class 1 disks, which I've put here on the title slide, which I think are a real frontier in planet formation. And I think, There we go. And where I want, before I get going into the actual talk, I should say that unfortunately class 0 and class 1s are a really big subject. You could imagine that a lot of the sessions we've had over the course of the week, polarization, chemistry, demographics, planetesimal formation and such, these could all in some ways have their own invited reviews in their own right. And so I'm not going to be able to cover every single topic. And to be honest, there's several that you probably wouldn't want me to talk about, or at least I wouldn't want me to talk about because I'll probably embarrass myself. So a few topics that I'm not going to be able to really talk too much about today, but I want to highlight because there are a lot of really great talks that have been contributed out there that I'd encourage you to check out are chemistry. You really wouldn't want me to talk about chemistry, but there's a lot of really great talks there. Outbursts, young stars tend to be found to exhibit these extreme brightening events that we think might be related to outbursts of accretion onto the star. And naturally, you can imagine that might have an effect on the conditions in the disk, which could ultimately affect planet formation. And multiplicity as well. And there was already a talk on this to some degree yesterday, so I won't be able to touch on these all that much today, but I really encourage you to check out all of these talks. And I'm going to sort of focus a little bit more on where my comfort level lies, which is going to focus a little more on millimeter continuum observations. And before I get to the class 0 and 1 disks, I think it'd be useful to step back for just a second and motivate why we're starting to get particularly interested in these young class 0 and 1 disks. And I think one of the legacies of the last 5 years since HL Tau has really been these observations of substructures in protoplanetary disks when observed at high angular resolution, and sometimes not even at all that high angular resolution. And we've really been finding, as far as I can tell, that whenever you look at a basically whenever you look at a protoplanetary disk with high enough angular resolution, substructures seem to be abundant. And I don't think I'm hopefully not spoiling too much for the next talk, but this certainly seems to me to be an indication that by the time you get to the protoplanetary disk stage, protoplanetary disks are really a significant amount of planet formation or what have you has already happened. And so I'd argue that protoplanetary disks are really not primordial. There's been a lot of dust grain growth and disk evolution, maybe even some planet formation that's happened. And we've had talks that have sort of spoken to that over the last week. And so if we really want to start to understand the early stages of planet formation, where it all begins, then we need to go to younger disks than what we've been looking at so far. And so if we go back to our sort of classical picture of star formation, starting with a cloud that collapses under the force of gravity to form a star, on its way to becoming a protoplanetary disk, it goes through this phase that we call perhaps the embedded phase or the protostellar phase, where the disk has formed but is still surrounded by this collapsing, infalling envelope material for about 1 million years or so. So this is where we want to go if we want to start to understand the early conditions in disks for planet formation. And before I go too much further, I want to just say a little bit of a word on jargon, because I'll probably slip up and say a lot of different things over the next 40 minutes or so. Nominally, I'm sure we're all familiar with class 0 and class 1 disks, but these have also been called embedded disks or even protostellar disks. And that's as opposed to, say, protoplanetary disks or class 2 disks or planet forming disks. So hopefully when I say embedded or protostellar or class 0 and 1, this is what I mean, these early stages here. And before I get to those disks, I just want to take a moment to reflect and say, should we really be surprised that looking at these young disks is where we want to go to understand the initial conditions of planet formation? I think Laura mentioned this on Monday, but we often sometimes overlook the fact that HL Tau is actually a relatively young disk and tends to be classified somewhere between class 1, class 2, or flat spectrum. We think that's one of these maybe an object in transition, getting rid of the last remnants of its envelope. And so it's probably at the very least, not much older than 1 million years or so, and a very young protoplanetary disk. So maybe we shouldn't be have been all that surprised that this is sort of the frontier we're starting to push to now. So the three areas I want to sort of focus on throughout my talk mirror in a number of ways the talks that we've had throughout the conference. I'm going to spend a little bit of time talking about what we're learning about the demographics of class 0 and class 1 disks. Then I want to spend a few slides talking about what we know or perhaps don't know about dust grain growth in the youngest disks, before moving on to finishing with the substructures that we're starting to find not just in protoplanetary disks, but also in protostellar disks. And so I'll start off with demographics. Since this is a 5 years after HL Tower conference, I thought it would be fun, since we've seen this before for protoplanetary disks, I thought it would be fun to look back at what the status of, or the state of the art was before ALMA. So this is what I think is one of the largest, if not the largest, surveys of protostellar disks prior to ALMA. This is from the Prozac survey by Jess Jorgensen with the SMA at an angular resolution of a few arc seconds. It's not necessarily obvious from this plot, but one of the challenges at the time to trying to understand protostellar disks is that these sorts of resolutions, and really even as we go to higher resolutions, but really at lower resolutions, you have to worry about not just the disk, but what amount of envelope contribution is contaminating these observations, and can you really say this is the disk, or is this or some of this emission envelope? And that presented a lot of challenges. But now with ALMA, our view has changed really quite dramatically. So I've tried to collect in the last few days or so this is probably incomplete, and I apologize to anybody whose work I'm missing, what our sort of current picture of protostellar disks are now with ALMA. And you can see now we have these beautifully resolved images, things that are very clearly disks, some things that we don't actually know yet. In the case of B335, as far as I know, and somebody can correct me perhaps on Slack if I'm wrong, despite having observed this with the highest or almost highest angular resolution we can with ALMA, there's still no indication that there's a disk here. Or at least a rotationally supported disk. But you can start to see now we're starting to get these really nice images where disks are starting to become apparent. We still have to worry a bit about the envelope contribution, but it certainly makes it easier to have these nice high resolution images. And so I think in a lot of ways, the protostellar disk, our understanding of protostellar disks has sort of followed our understanding of the path that our understanding of protoplanetary disks has taken, in that, but just set back by a few years, in that we're now entering this era of large surveys of protostellar disks. And I'd say this is probably highlighted in particular by the Van Dam surveys led by John Tobin of Perseus and Orion, where over 300 class 0, class 1, and flat spectrum sources in Orion were surveyed with ALMA, and another, I think, 80 or so in Perseus with the VLA, and I think ALMA as well now. And also the Odysseus survey led by Lucas Cieza, which looked at, on top of all of the class 2 disks that it surveyed, 78 class 1 or flat spectrum sources. And then also other non-ALMA surveys that have been doing great work are the Calypso survey with the PDBI, looking at 16 class 0 sources, or the Masses survey on the SMA, I believe, looking at the protostars in Perseus as well. And so with these large surveys of more or less every single protostellar disk in a star forming region, we've really started to make progress on understanding the demographics of these young sources. And so I thought I would start off by showing what we know about protostellar disk masses. We've obviously had a lot of discussion on this already, but on the left here, I'm showing the cumulative distributions that we're starting to get used to looking at for the protostellar disk surveys that we've done. Excuse me. And so here on the right in pink and gray, I'm showing Perseus. class 0, Orion in the middle in blue, orange, and green, and Ophiuchus in red and purple on the left. And there's a lot to unpack here, as you can see. What I'd say is you have to be a little bit careful about the Perseus distributions here, because this is done with the VLA. And so you have to worry a little bit about how you extrapolate from VLA wavelengths to ALMA wavelengths and what you assume about dust opacity. And so on the other hand, the Ophiuchus sources were done, I think, at a similar wavelength, if not the same as the Orion sources. So it's a little harder to say. This might actually be a real difference. But you see we have typical dust masses sort of on the order of 10 to 30, medians of 10 to 30 Earth masses or so in your typical protostellar disk. We see a little bit of a evolution, potentially an evolutionary trend with the class 0 disks, perhaps the youngest disks being a little bit more massive on average than the class 1 disks, being a little bit more massive than the flat spectrum disks on average. And we see that both in Orion and in Ophiuchus, despite the two not necessarily lining up perfectly. So we see a little bit of evolution there. We also, if you look at the sources in the upper right here, sorry, this is a plot of the distribution of disk masses from the masses survey. This is from a paper by Anderson et al. And these actually line up quite nicely. These are actually relatively high. They line up actually reasonably well with the Perseus sources distribution over here, but you do have to be a little bit careful of that because I believe the resolution was a bit lower here. And so there might be some concerns about envelope contamination. But we do have some hope that the envelope contamination isn't too much of a problem for the Orion disks because the distributions actually line up quite nicely with what we find, or what I found in a paper a couple of years ago where I did detailed radiative transfer modeling of 10 class 1 protostars in Taurus. And so where we're really able to make sure we're doing a good job of separating disk and envelope. And so that gives us a little bit of hope that we can rely on these distributions. And so if we compare that then to the class 2 disk surveys, what we find is that these young protostellar disks are on average more massive than your typical protoplanetary disk. So we see that over here on the left. This is a plot from a paper by Jonathan Williams where he's looking at a comparison purely within Ophiuchus. And we see this trend of class 1 sources being more massive on average than flat spectrum sources being more massive than class 2 sources and so on. And we also see this if we look at other star forming regions too. So we say compare Orion here with Taurus and Chameleon and Lupus and your sort of standard set. And so this sort of speaks to that picture of perhaps disks start when they're young being more massive, and then over time, dust evolution happens, dust grains grow, maybe planets form, and you start to hide more of your material where you can't see it in the disk. And so coming back to this idea, I suppose, of the initial mass budget for forming planets, I know we've had a lot of discussion already during Ilaria's talk and then on Slack after and in the discussion later on or on Wednesday about whether class 2 disks have enough mass in them to form the population of exoplanets that we see. And I guess what I would say, and maybe this is hyperbole, I suppose, but to some degree that doesn't necessarily matter because we do know that at the younger stages in the class 0 and class 1 disks, there's more mass, they're on average more massive. And so I'd say that these young class 0 and class 1 disks are a better representation of the initial mass budget that's present in disks for forming planets. And just for fun, I've shown a couple of comparisons of things that you might use to sort of gauge the planet formation potential of a disk, something like the minimum mass solar nebula, or the mass of a giant planet core, or the mass of a super Earth that we know are quite plentiful. And you see that in all cases, the embedded disks here in blue and orange show more disks that have enough mass to form each of those. Obviously, the usual caveats about opacity, what the efficiency of turning dust into planetesimals and such all apply as well here. And if you want to see a much more rigorous comparison than my simple just posting a couple of numbers on the distributions, you should go check out this poster by Lucas Tykonik, who's taken a look at how the more careful look at how the masses in class 0 and class 1 disks compare to the distribution of the masses of exoplanets that we know of, and does indeed find that we can do a much better job of reproducing those numbers with the class 0 and class 1 disks. I do want to speak for a second on this other aspect of young embedded protostars that doesn't always necessarily get as much attention, but there's also this extra reservoir of material in these systems in the form of the envelope, which could naturally affect planet formation. Not only could it be potentially an extra more material that could go towards the formation of planets, but we're also starting to see this picture of streamers evolving as material accretes from the envelope onto the disk. That could naturally obviously play an important role in the dynamics and the evolution of young disks. So I won't say too much more on that, but there's a whole lot of really great talks that I think and posters that I think you should check out if you want to learn more about that. So I'll just say that and highlight those over here. And then I want to say a word or two about protostellar disk radii as well, because we're now starting to get to the point where we have high enough spatial resolution that we can start to resolve large samples of these disks. And what we're finding in much the same way, I think, as the protoplanetary disks, is that protostellar disks, at least in the dust, are also perhaps turning out to be smaller than we expected. So on the right here are results from the Calypso survey, which found that only about 25% of class 0 disks were larger than 60 AU. And then on the left here are the results from the Van Dam Orion survey, where we found median disk radii of about 50 AU here for the class 0s, 40 AU for the class 1s, and 30 AU for the flat spectrum sources. So it is sort of interesting, actually, that we see this potential signature of decreasing disk sizes with evolutionary state. I would say that if I remember right, the distinction between the class 0s and the class 1s isn't statistically significant, but it is for the flat spectrum sources. So there may be some indication of disk sizes decreasing with time, but we do have to be a little bit careful about how we interpret this, because obviously these are dust sizes and subject to the different evolution of dust grains and radial drift and such. So then moving on to what we understand about dust grain growth, I want to spend just a few slides on this. And in some ways, it's just a few slides because I'd say we're not yet at the point where our surveys of dust grain growth are really quite mature in the same way that perhaps protoplanetary disk studies are. But we have known actually for quite a while that spectral indices, which are sort of your basic or standard way of trying to get some understanding of dust grain growth in class 0 and class 1 disks, do seem to be low. So this is a plot from Luca Ricci's paper a decade ago, where he also compiled the class 0 sources from Prozac, the Prozac survey, and the class 0 sources from a paper by Kwan et al. And they did indeed find beta values that are sort of between 0 and 1, which are low. And then more recently, this is a paper from a plot from Lucas Tykonik's paper, where he compared the spectral index between VLA observations of Perseus disks and ALMA observations, and also found that the spectral index seems to be sort of in the 2 to 3 range. So there's some indication here, I would say, that beta values in young disks might be low. I'd say we haven't yet gotten to a point where we've done a super careful job of accounting for optical depth and so on, where we can really definitively say much about it here. But there's at least some indication, perhaps, that the bulk population might have some amount of dust grain growth. Also, what's been interesting is that there's been some surveys that have found indications potentially of dust grain growth, or at least millimeter-sized grains being present in the envelopes of protostellar disks or protostars. So if you look here, this is from the Calypso survey on the left, but the same thing is being shown up here on the right. This is a plot of baseline versus flux for two different wavelengths, and what you see in blue shows the beta value measured between those two observations. And what you see for at least a few protostars is that as you go to longer baselines or smaller scales, there's some indication that the spectral index decreases towards 2 for at least some sources. So this raises the question are there millimeter-sized grains present in protostellar envelopes? And I think this actually, my understanding is, presents somewhat of a timescale problem, because it's not necessarily impossible to grow millimeter-sized dust grains in envelopes, but the timescale for that is much longer than we expect the lifetime of the envelope to be. And I would say this isn't necessarily present in all protostar systems. For example, over here we see no indication of dust grain growth, but there's perhaps some hints of that, and how those millimeter grains get there is an open question. But what I think is perhaps the most compelling evidence so far of large dust grains in a protostellar disk is this work by Daniel Harsono. Oops, I'm sorry, it was from 2 years ago, not this year, where he observed the protostar TMC1A at high angular resolution with ALMA, both in the dust continuum, which you see here in gray, but also in CO. And what he found is that there's actually this big hole in the middle of the CO emission from TMC1A. And so they tried to understand what could possibly be causing this hole. Ultimately, what it comes down to is optical depth. You need to have enough dust, I suppose, in front of the CO to hide it. And so one way they were able to make that happen is with a really large disk mass. Obviously, if you increase the mass, your optical depth goes up, and that would work. But they needed something like half a solar mass of material in the disk, which is, as you know, quite a lot. And so that would actually be really probably quite unrealistically large. You would at least expect the disk to be gravitationally unstable, which we don't see here. Another possibility is that the disk is really cold and flat, because if the temperature in the disk is cold, it doesn't get puffed up quite as much, and so you can put more of your CO emission behind the dust. But this seems to be at odds with what we know about the temperature structures of young disks, which seem to be much warmer on average than sort of your typical protoplanetary disk. And I point you to really nice work and talks being done here at the conference by Daniel Lin and Meryl Van 't Hoff, who talk about this more. Oops, sorry. And then the last possibility they came up with is that you could have large dust grains present in the disk. So if you have a lot of, say, millimeter-sized grains, that increases the opacity. And so if you have a lot of millimeter-sized grains, you don't need as much mass to drive the opacity up and to get a large hole in the center of your disk. And so this seemed to be the most promising avenue, suggesting that maybe large dust grains are present in the disk. And I'd also point, one question I have about this is how much your opacity prescription. We obviously don't know a lot about what the true opacity is, and your opacity can vary by a factor of a few depending on the assumptions you make. So I do wonder a little bit about that. Though I'm here, and it's not quite on this subject, but or not quite on the topic of TMC1A, but I'd point you to the talk by Daniel Lin, who's done has a really cool a study looking at measuring the opacity in a young edge-on disk. So what I would say, I guess, to sort of wrap up this bit is that we're certainly seeing some interesting evidence, or perhaps hints at the presence of large dust grains early on in protostellar disks, which is certainly intriguing for when you think about the onset of planet formation. And so the last thing I want to talk about with my remaining 20 minutes or so are sort of the abundance of substructures that we're actually starting to find, not just in protoplanetary disks, but in protostellar disks. And there's really been, I'd say, an explosion in the last 2-3 years or so of finding substructures of all sorts in the protostellar disk population at these earlier times. So we've seen a lot of the same sorts of features that we see in the protoplanetary disks, the rings and gaps, large millimeter cavities, spiral arms, maybe warps, and other things. And so I'm going to try and talk sort of broadly speaking about these different categories, but there are talks at this conference about a few specific objects. For example, IRS 63, there's a nice talk by Dominique Segura-Cox. For BHB1, I believe there's a nice talk by Felipe Alves. And for DG Tau B, there's a talk by Alois de Vallon, although I believe that's focusing a little bit more on the outflow rather than on the disk itself, on the substructures. And so I thought I would start by talking a little bit about the sources with these large millimeter cavities, or I think as we had some discussion on Wednesday, perhaps the new official name for the conference at least is these donut sources. So we're obviously seeing, this is the type of substructure we've seen the most, I'd say. We see a large range of properties. We see sources that have really small cavities, as small as about 10 AU or so, but also really quite large as 200 AU. Many of the sources have inner disks that show up at the center. And one of the interesting things I think about these inner disks, and it kind of leads to the next topic, is that if you look at the inner disk, in some of them, for example, you might even be able to see it by eye in HOP 65, it almost looks like that inner disk is a little offset from the center of the ring. And that, I think, leads to the question of, are these young sources actually binaries that we just haven't seen? And this is a question I know we ask a lot and have asked a lot at this conference already about the transition disks in the class 2 stage. And so for the sources in from my paper a couple months ago, we tried to tackle this by fitting an analytic model that tried to account for the ring, any asymmetries, and the inner disk. And what we indeed found is that it seems like if you look at the posteriors for the radius at which the inner disk is centered, it seems to be significantly offset from 0. And so that may be lending some support to the idea that these sources are young binaries, because if you have this inner disk being offset from the center, then you need something in there perturbing the young star, the star that disks around. And you would imagine that thing would have to be relatively massive to be able to push it fairly far. And so we did try to compare at least these sources for my paper a month or two ago with HST images to see if we could find any hints of a binary there. And thus far, I'd say we certainly haven't found anything. I'd say the results are also fairly inconclusive. In the most cases, the resolution is just barely enough where you might be able to possibly see something, but really not. So I'd say we haven't found any evidence yet, but there's a lot of other ways that we can look. And on that note, one really interesting case is this source of BHB1 from Felipe Alves' work this year, where they also, on top of looking at the disk with ALMA and seeing this nice cavity, they also had VLA observations at 22 gigahertz, where they see some sort of free emission associated with, or some sort of emission associated with this central star, but also inside the cavity, they see this tentative hint of a potential source that falls inside the millimeter cavity. So I think that's really exciting and a really interesting potential detection. In their work, they did some modeling of the planet, of potential source disk interaction, and found that if there was a planet carving the gap, it would have to be somewhere in the 5 to, I think, 70 Jupiter masses or so. So I'd say the jury is still out to whether this is a planet or is this a star. But it's certainly a really interesting source to keep looking at. And I'd say if you want to learn more about this, I'd point you to the talk by Felipe Alves. So what we've also found a decent amount of are rings and gaps. Obviously, these are really prevalent in the protoplanetary disks. And we're also really seeing quite a wide range in the younger disks of the properties of the substructures. So in the case of GY91 up here, we're seeing these really prominent rings and gaps. On the other hand, if you look at IRS-63, then the substructure is certainly much more subtle, as is sort of somewhat in between the case of DG tau B here. And you can see this even more so in the radial profiles that have been made where these structures show up really quite readily for GY91. But there are a lot, but the rings and gaps in IRS-63 are really quite shallow, and that's really interesting. I don't know if this is telling us something about the substructure formation process, or if this is just the case that we have just a few disks, but there's a lot to be learned here. I was really impressed, actually. I think GY91 is a particularly exciting object because there was a paper by Lucas Cieza last week that came out that had even higher angular resolution observations as part of the Odysseus survey. And so when he observed GY91 at even higher angular resolution, we can see even more substructure starting to show up. So the middle ring, which actually when I originally looked at it, we found to be quite wide, breaks up into 2 separate rings. So now there's 4 total substructures in this young disk, 4 total gaps, I suppose, in this young disk. But also there's some hints that in the innermost region of the disk, excuse me, that there may be in the inner 2AU or so, there may be a hole in the disk. So there's some sort of cavity as well. So possibly as many as 5 substructures or more if we continue to look, I suppose, at even higher angular resolution someday in this particularly young disk. So that's quite exciting. And I guess I should say, I'd point you to the poster by Lucas Cieza if you want to hear more about that. And then we're also starting to see other types of substructures that I've kind of generally classified perhaps as other. So we're seeing asymmetries show up in a lot of, say, the sources with cavities. You see asymmetries here and here, and so on. We're also seeing spiral arms. This is in the disk of HH111. We see these 2 spiral arms show up, and the authors suggest those probably come from this really massive gravitationally unstable disk. We see potential hints of a warp in the disk of L1489 here. And then in L1527, there's potentially some hints of substructure that I don't know exactly how to classify because we certainly need higher angular resolution, but there may be some hints of substructure there as well. So we're really starting to see sort of an abundance of substructures in protostellar disks. I won't have too much time to speak about it, but I did want to say that we're also seeing a lot of interesting substructures in young multiple systems. So I'm showing a gallery here of just a few examples of that. And obviously, these sorts of substructures are going to be important in understanding how planets form around multiple stars. Obviously, we know that planets form around multiples. And so any substructures present in those disks are naturally going to be important for understanding how that process occurs. And so I'm not going to say too much more about that, but I would point you to talks by Morera and Shige Takakua to see more about that. And of course, there was the great talk on multiplicity yesterday as well. So with my last, I suppose, 10 minutes or so, what I wanted to try and do is give you my perspective on this question of how early do substructures form in disks. And I know to some degree you say, okay, we've seen substructures in protostellar disks, so we know that they form in less than 1 million years or so. But 1 million years is really quite a long time, and there's a big difference between substructures forming in, say, 100,000 years versus substructures forming in 500,000 years versus substructures forming in 1 million years, taking really the full 1 million years or so. And so I'm going to try and sort of lay out what my view of sort of the timeline might be. And so the typical way we do this is we typically try to use class 0 and class 1 as this evolutionary tracer, with the class 0s and the class 1, the class 0s being the youngest sources with a really massive envelope, and then the class 1s being a little bit younger. or sorry, a little bit older, and then flat spectrum sources being older still. But I did want to take just a moment to point out we do need to be a little bit cautious about that. And we've sort of known this for a while, but viewing angles can, and how you're seeing the source can obviously play a role in how you classify that. This is a plot from some upcoming work that I'm doing radiative transfer modeling of a lot of the protostars from the Van Dam Orion survey. And we do see, though there's a lot of scatter, a trend that a correlation between volumetric temperature and inclination. So we do need to be a little bit careful about just purely using class 0 and class 1 as a pure evolutionary tracer. And so what I've been trying to do recently, rather than looking at something like class 0, class 1, and I think a few of us in the field have been doing this, is trying to have a more holistic picture of the protostar and disk and envelope system, and use what we're calling perhaps the embeddedness of the system. The ratio of the envelope mass to the disk mass as sort of to give you an idea of how old or young. And this generally traces fairly well with volumetric temperature and other things that you might use to classify the systems. But you can imagine you would expect roughly, and this is probably not monotonic or necessarily purely decreasing, but you would expect with time, your envelope is going to deplete onto the disk and potentially star eventually. And so you would expect with time that really old, really young disks have a really massive envelope, potentially compared to their disk. And then as you get older, that starts to go down. And the way that we try to do this is by putting together these sort of complete models of the protostar that accounts for the millimeter emission, the SED, and so on. And in some cases, you can even see, for example, over here on the left, that there's this massive envelope when you go to really large scales in the visibilities, where we can kind of put together a picture of how big the envelope is compared to the disk. And so if we start to put sources on this diagram, I'll start with the embedded the disk with cavities, because that's the paper where this came from, this template came from. We see that there's a sort of a big range already in the quote unquote donut disks, where there's a lot of relatively old sources, but we also see a few that are really quite embedded still in a fairly massive envelope of material. There's a few sources, WL17, GY91, DG-tau-B, and BHB1, all seem to be sort of relatively older compared to a lot of systems. They seem to be sort of toward the end of the embedded phase, perhaps close to losing their envelopes and becoming your typical sort of protoplanetary disk. In the case of WL17 and GY91, these numbers come from radiative transfer modeling that I've done. And in the other case, it's perhaps a little bit more speculative. So I've put a fairly large range there, but that's roughly sort of where we kind of expect these disks to lie. And then IRS 63 has had some modeling done, and it seems like it has an envelope roughly comparable to the disk mass. So it's somewhat moderately young, and certainly younger than those other sources. And then there's sources like L1527, L1489, and HH111 that seem to be also really fairly embedded in a relatively massive envelope. In the case of L1527 and L1489, that comes from modeling that's been done. And admittedly, in the case of HH111, that's a little more based on its classification, I believe, as a class 1, or I believe a class 1 system. And so you can break this down into the different types of substructures. So we see the rings and gaps. I'm showing the rings and gaps here, where we see, at least in the case of GY91 and DG-tau-B, these seem to be somewhat older. IRS 63 is perhaps moderately young, but we don't really see too many sources that seem to have this really massive envelope, suggesting that the source is really quite young. IRS 63 is probably the record holder here, and it's young, but not crazily embedded, I suppose. If we look at the cavities, we see a much larger range, perhaps a tendency towards the older disk, but we do see at least 1 or 2 sources that really have these very substantial envelopes, suggesting that perhaps cavities can form quite young, and that might fit with this picture of some of them being young binary systems. And then the quote unquote others, I suppose, tend to fall in this towards the older range here with relatively massive envelopes, and these seem to be decently young sources. And so I put them all back there. Then I think the last thing I should say, I suppose, is we need to be somewhat careful about how we interpret these trends overall, because obviously this is still a very biased sample. We only have a handful of disks in each classification, and we really haven't yet done a comprehensive survey where we, this is in many cases based on just a handful of disks. So I think we should be a little bit careful of any trends that we interpret from this yet. But it's certainly telling us some fairly interesting things. And so I just wanted to talk about one possible proposal that's been put out in this paper by Lucas Cieza last week, which I think is interesting. And I'm taking a plot from his paper, and I think I'll mostly talk about the left side of this plot briefly. But if you want to learn more, I would certainly encourage you to check out the poster that Lucas has on it. And what they propose in their paper is that substructures start sort of in the early phases they start to form in the early phases, maybe with something other than planets, and that the substructures, we should see that in these young disks, really young disks, are relatively shallow as they start to build up, and over time they get more and more significant, they get deeper and wider, and then by the time you get to later stages, they start to show up as more prominent gaps and rings, and then so on and so forth. And I've put stars next to the sources that we tend to classify as embedded in this case. And that generally seems to fit with this picture that we're seeing thus far, where a lot of the young disks that we've looked at with super high angular resolution seem to either have no substructures or very shallow substructures like IRS 63. And then as you get to slightly older sources like GY91, they start to get more prominent. And so that seems to generally fit with the picture that we have that is starting to emerge. But I should say again that this is based on really only about 4 or so disks that have been observed with super high angular resolution. So we should be a little bit careful, but it's certainly an interesting possibility. So the last thing I want to do then is to turn this back around on you all, and I've created a poll to ask, when we start to look at more embedded disks with the highest resolutions we can with ALMA, what do you think we'll find? Do you think we'll mostly find smooth disks, very little substructure? Do you think that we'll mostly find sort of shallow rings and gaps, sort of like what we see in IRS 63? Or will you really start to find this population of disks that have deep rings and gaps, more like GY91, but at younger stages? Or maybe we'll find mostly spirals and asymmetries and other things, or maybe some sort of mix. And rather than try to give you every possible permutation, perhaps if you want to pick a mix, you can elaborate more on Slack. So to wrap up, I think just a few key points. We've now starting to get to the point where we have a good picture of the demographics of young embedded disks, and we're starting to see that young disks seem to be more massive than class 2 disks, and also perhaps smaller than we expected. There's some indications that maybe there's been dust grain growth already in the early stages, but I think there's still more work to do here. And then certainly we're starting to find a really interesting picture of substructures in the youngest disks that is certainly raising a lot of questions about planet formation at early times. So I think I will stop there and let you all fill out the survey, and I'm happy to take any questions.
Thank you, Patrick. That was a wonderful review of these younger disks. It's really interesting to see all of the structure that it's now observed in these young disks. I mean, this is something I was not expecting, at least. Okay, so now we have the results of the poll. I guess people are still answering. So far, mostly shallow rings and gaps.
Yeah, so there's a good mix here. I see a mix, so hopefully we'll see some discussion on Slack, and I see also some preference for spirals and other things. So nobody seems to think there's going to be a lot of deep rings and gaps, though. So that's interesting. I'd say I have to largely agree with what's found here, but I guess we'll have to see what comes up.
We have a competition there. Yeah, no, a mix is winning. Okay, well, people keep answering this poll. We have a bunch of questions on Slido. So let's get started. So the most voted question so far from Dominique Segura, what ideas do we have for deciding where the edge of the class 01 gas disk is? Can we decide where disk ends and when envelope begins?
Yeah, so that's a really good question. And I don't know if I'd say I have a good answer. So typically, I suppose I guess maybe for some background there, it's very difficult I mean, dust it's a little bit easier because of optical deficits, but when you get to the gas, because lines, your typical CO and even C13CO and sometimes C18O can be relatively optically thick, can be very optically thick in the envelope. It gets very difficult to disentangle what's envelope and what is disk. I'd say right now, probably the best way that it's being done is by taking these position velocity diagram along the major axis of the disk, and you can look at essentially what the velocity profile is. And in a number of disks, we've seen sort of a typical, r to the minus 0.5 power law, indicative of Keplerian rotation. And then when you go out far enough, eventually you see a break, and that break to a steeper power law, and we have tended to associate that break with the transition from the disk to the envelope. And that's, I'd say, probably how most of this work has been done lately. And there was actually a nice paper last week that I haven't had a chance to look at yet from Yusuke Eso, where he's examined this, how well this can do at reproducing disk and properties. And he suggests it does quite well. I have some concerns because you're sort of inherently collapsing a three-dimensional position velocity information into one dimension and then trying to extrapolate from that. So I think there's probably still some questions there. Certainly, if you can get sort of higher spatial resolution observations of less abundant isotopologies, you can worry less about the envelope, something like a C18O, or if you go to even maybe a fainter isotopologies, you have to worry less and less about the envelope. But of course, that takes more and more observing time. So I can say I've been working on doing some sort of more full radiative transfer modeling of that too, and I don't have too many results to say, but that's kind of a smorgasbord, I suppose, of answers that doesn't fully get at it, but hopefully helps some.
Yeah, actually, that was a question that I have. Like, how often can we actually disentangle the envelope from the disk? I mean, in my mind, I have like the idea it's only a handful of sources, but I think that's changing quickly, right?
Yeah, it's been a handful. It's going up quickly, and I'd say everybody has a different. But I think there was a paper by CUAN a couple of years ago that did this for a good number of young sources, at least with this position velocity diagram method. And so it's starting to get up there, and ALMA has really helped with this because we can start to move beyond just CO and 13CO and start to see fainter things where the envelope becomes less of a problem.
Okay, we have another question here, lots of votes. So what is the possibility that the millimeter grains in protostellar envelopes were inherited from the ISM?
I guess that's a good question. I suppose I'm not tremendously familiar with the literature, but so I'm not sure if there's been a lot of evidence of millimeter grains in the ISM. So I may have to defer to somebody that knows better than I do about that.
Yeah. So kind of related.
It seems like densities would be a little low to grow them there, but somebody may be able to prove me wrong on Slack, perhaps.
Sure. So there's another question from Jake Simon. So is there any reason to expect millimeter size grains not to form as soon as there is a disk in place? So what would be stopping it?
I don't think anything is necessarily stopping it, and you would expect, I'm trying to remember, I think the timescales for growth of millimeter grains in disks is good. I suppose one thing that could stop it is if you could imagine these disks being really massive and gravitationally unstable. Perhaps that might keep them sort of puffed up and prevent some of the settling. So I suppose I could imagine some things. I think the other question is just, until we, so perhaps the question would be, maybe it'd be more interesting if there's not millimeter grains in young disks. I suppose I come at this from an observational perspective of we just don't know yet, but I could imagine a few things that might stop it, or potentially it might be interesting if they simply don't have any.
Yeah. This is an interesting question. So what fraction of the class 1 sources have substructures, like gaps, cavities, spirals, I guess, as well? Is the incidence of these features as high as in class 2 sources?
So we haven't, I can put a lower limit on it. I would say so because we really haven't had enough surveys, I suppose, with high enough angular. For example, the Van Dam Orion survey, the resolution was something like 30, 40 AU. So we're really only seeing, the biggest substructures. So there really hasn't been a uniform substructure. So, I could put a lower limit in the Van Dam Orion survey. We had 7 disks out of 300. So what's that, 2%, 3%? But that's definitely a lower limit. I can say, I guess WL17 and GY91 came from a survey I did of Ophiuchus that had something like 10 disks in it. So maybe that's more like 20%, but I'd sort of put these at lower limits rather than a solid constraint on what the fraction is. And we definitely need more high angular resolution observations of these sources.
Yeah, I think as soon as we go to higher resolution, we start seeing something. So, okay, another question. Do we expect envelopes to dissipate at the same rate for different sources?
I would say probably not. And I think there's been nice simulations. You probably can look at simulations by, say, Michael Kufmeyer or Matthew Bates simulations. But, I think it's probably not going to dissipate at the same rate, and there might be, say, replenishment as these systems are don't evolve in a vacuum for the most part. There's a whole star forming region, and so I would say probably not. And so you have to be a little careful of that, particularly when you're doing some of these interpretations of envelope mass to disk mass. But to some degree, you would suppose that expect with time that they would decrease.
Okay. Another very voted question. So the 2 plots on class 0-1 disks seem to show the opposite trend. So size decreasing over time in the paper of Tobin 2020, while increasing in the paper from Mori 2018. Is that correct?
I guess the plots do seem to show that now that I think back to them. I'm trying to remember. I'd have to look back carefully at the paper from Mori et al. Because the survey, the Calypso survey, I believe, was only looking at the class 0s. So I'd have to look back at where actually the class 1 measurements came from that they plotted there. So I'd have to double check that. I would also say one thing to be careful of there is I think the Calypso survey tended to look at sort of the well-known young stars. That somebody can correct me if I'm wrong on this, but they sort of tended to look at the well-known young sources rather than a sort of just a totally uniform one star forming region. So we may have to be a little bit careful about interpreting things there too, though perhaps it's less clear what you'd expect for disk radius. But I'd have to look back at where those class 1 sort of points actually came from.
Yeah, we can maybe discuss that on Slack later. Trying to choose between the many questions. So here's a good one. Is the ratio between the mass of the envelope and the mass of the disk more reliable than the volumetric temperature as an evolutionary tracer?
That's a good question. And I suppose I don't know if I have a great answer to that. What I would say is that we know at least when you're looking at things like when you can put together this picture that includes a lot of different data sets like ALMA, where you have the spatial information and the SED and whatever else, you can certainly you're perhaps less, maybe what I'd say is you're less likely to have problems. Like you can't accidentally have a really edge-on disk that you classify as, say, class 0 because it's so edge-on that no infrared emission gets out. Whether it's more reliable, there's obviously problems with it too. Do the envelopes decrease uniformly with time? Really, I think what you want to look at is perhaps a sort of holistic picture where you have an idea of what the stellar mass is, what the envelope mass is, what the disk mass is, and how that's all evolving with time, and perhaps even some amount of environment, is it gathering more material. So I don't know if I'd say it's more reliable necessarily, because they both have their problems. And I also wouldn't try to put actual times on any of these, just to, you can use it as a rough guide. And I can say it has less issues, I suppose, with viewing angle, but might have other issues. They generally, I didn't show it there either, but generally, if you look at envelope mass to disk mass ratio and bolometric temperature, they're generally correlated. So they're telling you something similar, largely.
Yeah. Maybe one last question. How is the disk radius defined in this plot? Is it the radius enclosing a certain flux fraction? Yeah,
so that's one of the things you have to be careful about. That's to some degree why I didn't try to show any comparisons with the protoplanetary disks, because unless you do this all in a uniform way, it's kind of a mess. So what Tobin et al. Did in this case was look at, did a Gaussian fit in the image plane and took the 2 sigma size of the major axis as the radius. And we actually did a comparison there where we looked at the flux enclosed in 90 or 95, within 95% or so or the radius in which encloses 90 or 95% of the flux. And generally speaking, they were correlated and gave similar answers, but not, it wasn't a perfect correlation. So that's how it was defined in Tobin et al. In the case of the Calypso survey, what they did for the most part, I believe, instead is they essentially what you look for is where the visibilities as you're going from short baselines to long baselines start to flatten out, and that can kind of put a constraint on the size. Not all of their disks were resolved, if I remember right, but you could certainly say based on where that flattening out happens and where you don't see any more resolved structure, roughly what the size of the component of the compact component in there is. But yeah, so I think it would be worthwhile at some point to do a more uniform analysis of class 0, 1 sizes and class 2 sizes using some sort of comprehensive similar or the same technique for all of them, so we can start to get better information about how that evolves.
Yeah, get some consistency. Okay, well, thank you so much, Patrick, for a wonderful talk and for answering all of these questions. So we're going to move on now to Andrea Isela.
Hi, can you hear me?
Yes, we can hear you.
Great, let me share my screen.
Perfect. So Andrea is going to tell us about the disk substructures in disks. Please, go ahead.
Yes, now I don't see the timer anymore. Give me a second. Okay, well, I would like also to thank the organizer for inviting me and for putting together this very nice, sorry, what's going on? Okay. For putting together the very nice conference and all the effort that it takes to have it remotely. So I'm going to talk to you a little bit about this structure. We have heard a lot about this structure in the last few days, and as you may have realized, there have been a huge amount of work done in the last 5-6 years before and after the beautiful image of Tau. And in this conference alone, there is a staggering number of talks and posters. So for the next 10 hours, I'm going to go through all of these and describe exactly what all these people have found. Okay, I'm obviously kidding here. So instead, what I'm trying to do is to give you a partial overview of what I think are the main results. And I apologize because I'm sure I will leave out a result of many people's. So, but that's I try to do my best here. So particularly, I would like to talk about these 6 main items in my talk. I'm going to review what we know about this structure as observing millimeter and centimeter dust emission in continuum. The structure observing scattered light, which are also very important. So this is mostly optical and near infrared, thanks to the really amazing new instrumentation that allows you to reach high contrast imaging at this wavelength. And but the big elephant in the room, I think, is the structure in the molecular gas emission. We have talked a lot about, we need to know what the gas, where the gas is, how much gas you have, and what the gas is doing. And so I think only when you combine these multi-wavelength observation, you can get a complete picture of the structures and substructure in disks. I will briefly go through the origin of this substructure. This was already covered by Paola Pinilla review talks yesterday. And I think, there are still many open questions. And so my point 5 is really what are for me, at least the main open question and how we can address them in the future. And because we're getting close to Christmas, I will finish with my very personal Christmas wish list and see how that goes. Okay, before talking about substructure, I want to make sure we are on the same page in terms of structure, general structure of protoplanetary disk, and the fact that depending on the wavelength you use to look at the disk, you see different things, right? So this should be very well known, but it's very important in terms of substructure. This is a picture from the review chapter in Protostellar Planet 6. This is where you see, our Donald looking like disk, and the disk is there is plenty of dust and gas, and particularly the dust makes the disk very optically thick to optical and near infrared wavelengths, so that when you look at the disk in the near infrared, for example, in scattered light, what you see is only the superficial layer of the disk. So really the tiny atmosphere down to an optical depth in the visual of about 1, okay? Which doesn't take much dust to get you to that kind of optical depth. As you go in the millimeter, you are sensitive to larger grains. So typically, if you talk about dust continuum emission, the grain size that you're sensitive to depends is roughly corresponding to the wavelength. So millimeter and centimeter, you're looking about, you're probing sub-millimeter, millimeter grains. They settle toward the disk midplane if there is not much turbulence in the disk, and the disk becomes more transparent. So when you look with ALMA, for example, then you see what's going on in the disk midplane. The molecular line emission allows you to essentially to join these two tracers, because depending on what line are you using and depending on the optical depth of the line, you can either probe the very upper layer of the disk, for example, if you use optically thick line like 12CO, or the more optically thin midplane, if you use an optically thin line. But in general, a line emission has both an optically thin and optically thick component. Even at 12CO, there is an optically thick component in the line. So line emission generally tells you more about the entire structure of the disk, both vertically and radially. So with that said, let's start talking about structures in the millimeter wave. And on Monday, Laura showed some beautiful example of how much ALMA really improved our understanding of substructure. And she showed a comparison between karma images of HL tau and ALMA images of HL tau. This is another one of my preferred comparison to show people really how much ALMA allowed us to just see a very sharp view of the disk. This is a relatively famous object, MWC 758, an Herbig star. Observed this guy quite a long time ago with the SMA and karma as well, and that's what you see. Two blobs. So structure were not a discovery of ALMA. So structure in disk were already known from Plateau de Bourg observation, SMA, and karma. But most of the time, the only thing we see were blobs. And now this is what you can get with ALMA when you have a resolution of about 10 times better than what was achieved before. So ALMA really was a revolution for looking at dust continuum emission and also molecular gas emission. And you have seen this image 20,000 times we are on Friday at the end of the conference. D-Sharp was the first large effort to try to observe a relatively homogeneous sample of object, and the main discovery was that clearly substructures are ubiquitous in the most massive disk that we have observed. A recent paper by Lucas Chiesa that also show the similar object and similar structure in Ophiuchus. And again, you see the predominance of rings and some asymmetries. And also the beautiful survey in Taurus performed by Feng Long, where again, this is a subset of the most massive disks. Sorry. And the most massive disk. And here again, you see a predominance of rings and structure, and very few, if not none, of this object is really smooth, okay? So this has been mentioned yesterday, if I remember correctly, but I want to make sure this is very clear that, so far we have looked at very biased sample, and particularly we have looked at the most massive disk, okay? This was nicely shown in this recent paper by Lucas Chiesa, where you see the number of objects. This is for Ophiuchus, but very similar can be said for Taurus, for example, or other region. And most of the disks in Ophiuchus, they have a low millimeter flux, meaning they tend to be smaller, they tend to be less massive. But because due to the observational bias, and because it's clearly easy to observe large disk and small disk, the object that we cover in the D-Sharp and also in the other, most of the other survey at high angular resolution really focus on the most massive disks, okay? So I think we have to be careful in extrapolating the result of this very biased sample of massive disk to the general structure. So one question can be why, if these regions are coeval, and so what is the reason, why there is a tail of massive disks, okay? Are these because these disks maybe have lower viscosity than others, and so they didn't evolve fast enough? Is this because they just form with higher mass? And so, but the reason why there is a tail of massive disk may have strong consequences on having structure, right? So it is really important now to extend the observation toward the small mass disk. This has been done to some extent. This is again from Long et al. 2019. And when you go to this, when you look at this low mass disk, small disks, as I said, they tend to be smaller in radius, right? And then the number of features you see drops substantially. Okay, well, as you can see from the comparison between the size of the images and the beam, which is this white ellipse down here, these objects are clearly spatially resolved, but they are spatially resolved in the same way disks were spatially resolved, for example, with Karma on SMA 10 years ago, 11 years ago. And Laura showed this picture of old observation where all the disks that now show beautiful structure were just blobs, okay? So the fact that you don't see structure yet doesn't mean that they are not there. It means that we need high angular resolution to really investigate whether they are there or not. Okay, so with the caveat, keeping this caveat in mind that we are looking at the most massive disk, okay, these are some of the properties of the ring we see. The first striking characteristic is that all these objects look different one from the other. Okay, it's really difficult if you try to categorize rings. it's really difficult to come out with a few typical characteristics. These are from Jane Wang and Feng Long again, and so you see, for example, here the radius of the ring as a function of the mass of the star. One could expect that there is a correlation there, although we are looking mostly at low mass star, although we have some Herbig star, and we don't really see any correlation. And in addition to that, rings cover a huge amount of radii, all the way, from the largest ring we see, 160 astronomical unit, all the way down to the resolution of our telescope. And there are rings at small distances from the star, okay? The gap width, I'll talk more about the gap width later, also is very diverse, okay? So there are really no specific feature except that there is a very large variety of properties. I want to point out that there are structures at very small separation from the host star. Okay, so on Monday, Didier Queloz said, well, you still don't have the resolution really to tell to probe the terrestrial planet forming region, to probe where most of the planets are supposed to form. Assuming that most of the planets form within, say, 10 astronomical unit, and this is partially true. But we are getting there, okay? So, well, this is the famous example of TW Hydra, where there is a gap at 1 AU. Clearly, this is a peculiar object because it's the nearest disk to Earth that we can resolve so well, and so this help us improve the angular resolution. But even in the disk, at the distance of 150 parsec, there are structures in the innermost region. This is HD 16396, one of my best friends. And now if you zoom in, there are features on 5 to 10 AU scale. And clearly we have to do better than this, right? This is where you really hit the limit, or we will hit the limit of angular resolution that ALMA can provide. And I want to point out, the Jeff Jennings talk about, using different ways to deconvolve the images. For example, using this code Frankenstein that may, seems to reveal that there are more structures, particularly in the inner part of the disks, okay? So, but there are structures at a very different radii. Multiplicity is another important topic. Rings come in very different forms. Some disks show many, many rings. Some other disks show maybe only one ring. So we have tried in the last few years to really try to understand these rings, right? And so when you see rings, what do? You try to fit them in some way. And I think this is difficult because there are really different types of dust rings, right? There are, these are 3 examples. AES 209, very narrow rings, a lot of rings, at least the 2 outermost rings, extremely narrow, extremely well defined. This is probably, the most intuitive definition of a dust ring. But then you have things like SR4, where it's more like a gap than a ring, right? There is clearly a ring here, but the ring is much wider, much flatter, and it's very different from the narrow ring you have in AS29. And the third class of rings are things like Elias 24, and there are a few more where you have a narrow ring overimposed to a much broader and wider ring of dust. And there are these central component which might or might not show features depending on for example, the optical depth. So you see a shallow feature in AS209, for example, shallow rings. So it's really difficult to analyze in a uniform way the rings because they have very different features, very different structures. Nevertheless, the easiest way you can try to analyze and study this ring is by assuming that they are Gaussian. Okay, we do that all the time in science. Whenever you have to pick some functional form, Gaussian are always the first you think about. And this was done by, in the D-Sharp paper led by Kees Dullemon for a few of these rings. So this is your intensity profile, for example, HD 160-26 and HD 1430-06. And you can fit Gaussian rings. You can take into account the fact that there is a beam, so you have to deconvolve. your intensity profile. And what you find, what you measure is, for example, the radius of the ring clearly and the width of the ring. And the width of the ring is very important because the width of the ring is directly, or at least can be directly connected to both the formation of the ring, but perhaps more robust and solid is really what the ring is in terms of dust properties and in terms of the coupling between dust and gas. So these are the results from Key's paper. You can see so there are so the dots are the width of the ring, where the width is the width of your Gaussian. The other line that is important here is this orange line. Okay, the orange line with this gray region is the pressure scale of the disk at the position of the ring. And the reason why it's important to compare the width of the ring with the pressure scale of the disk is because that's where really most of the physics of the dust and gas coupling is, right? So if you see structures that are much smaller than the pressure scale of the disk, it means that the dust is decoupling from the gas and is moving toward the pressure, the peak, possibly to the peak of a pressure that is located at the position of the ring. Right? If you find structures that are of the same scale, it does you don't have, for example, the strapping, but perhaps may suggest that there is more coupling, either because the dust grain, the gas density is larger than what you expect, or, for example, there is more viscosity, or the grains are smaller. So your Stokes number is essentially the dust Stokes number is smaller. So it's really important for understanding the physics of this ring to compare the width to the pressure scale of the ring. And in some cases, you see, we measure widths that are smaller than the pressure scale. I have to say that, clearly the pressure scale depends on the temperature in the disk, which is not very well known, and that's why there is an uncertainty region here. But in some cases, we have good evidence that these rings are extremely narrow, and I would like to go back to AS219 because you can appreciate with your eyes, if you compare these rings with the beam size, how narrow these rings are, really narrow. Okay. So there is a caveat also. Clearly, the fact that you have large rings, it doesn't mean that these are single rings. Actually, ALMA observation have told us many times that when you see large rings and you go and look at it at a higher angular resolution, most of the time, this large ring will split up in smaller rings. One clear example that I don't have a slide is, for example, K-calcium 15, right, where the large ring in the K-calcium 15 is a combination of smaller ring. You can see the paper by Stefano Facchini, for example, about that. So keep in mind that caveat. So when you do this analysis, the fact you see large ring, it doesn't mean that they are single rings. One other important aspect about the dust ring is how much mass there is in the ring. And so the optical depth at the millimeter wavelength is pretty large, okay, less than unity, but more than 10%. And this is because there is quite a lot of mass, right? So this plot down here shows the dust mass in some of this ring, again from Key's paper, and the number is just to remind you about the orbiter, so the radius of this ring, right? And what really I found extremely interesting is that these masses here is 10 Earth masses, 100 Earth masses. This ring contain enough mass to form planetesimal at very large distances from the raw star, and this is really a shift in terms of how you form planet and planetesimal in disks. The solar system has been the only example we had for very long time. And the solar nebula model, all the mass in the disk is within 10 AU. Okay, and if you based on this, say, old model, there is no way you can form planetesimal at 120 AU. Okay, there is really no way you can do that. But ALMA observations are showing us that you can retain enough mass of solid to form planetesimal in the very outermost part of this ring. So, and I always wonder about the implication, for example, also for the solar system, and for the fact that we have a lot of trans-Neptunian objects of pretty large mass, right? So do they form there, or they get there after the formation of the solar system? And and this is independent on the formation itself of the ring, right? I don't really care how you form this ring, or the only things I care is that no matter how you form them, they can trap a lot of mass in the outer part of the disk. The caveat here is that dust masses could be largely underestimated if there is a large fraction of solid already locking to large bodies. If you have boulders, we are not going to see them in with ALMA. And so, and it's also true that we could overestimate the mass if we don't know the opacity, but I think it's more likely that we are underestimating the solid mass, okay? So this is pretty much all I want to say about symmetric rings, right? The other structure that ALMA has shown us is asymmetries in the dust continuum emission. Actually, no, you may go back and remember the famous paper by Ninke about IRS 48 with this staggering asymmetric feature. And I think it's, it's interesting that it's still probably the most asymmetric disk, at least in the dust continuum we ever observed, okay? So this is a compilation of asymmetries by the recent paper by Ninke van der Marel. And you see that what I want to point out, that the fraction of millimeter wave emission in these asymmetries really varies across the entire scale, from a fraction of a percent to almost 100%. So IRS 48, almost all the flux come from this big crescent. HD 14, 25, 27 is another very well studied, very asymmetric disk, a BioRig and so forth. MWC 758, you have two crescent. Sometimes you have a combination of ring and crescent. So these are very interesting objects. They are rare, okay? It's not that most of the disks show these asymmetries. And what I found particularly interesting is that this crescent and asymmetry are preferentially found around early type stars. There are observational bias, but I think it's pretty robust result that RBGA stars tend to be more asymmetric, not only in the millimeter, but also in scattered light and molecular gas emission. And that to me points toward the dynamical origin of this structure. Rossby wave instabilities is perhaps our only model we have so far to explain these large crescents as vortices that can trap particles. Rossby wave instabilities can be triggered in many ways, either by viscosity differences or planets. But again, forgetting for a second the origin, I think this technique is really seems to be the way you can form this asymmetric structure. The caveat here, and I like to highlight the caveats because this is all these caveats is where I think we can find space to work in the future. Is that, and as far as I know, and please correct me, I don't think we have any measurement of vorticity associated with these asymmetries. So we call them vortices because they look like them in dust continuum emission, but we have never seen rotation if you look at the gas, okay? There might be new results coming out soon for some of these. I know one of these in particular, but so far we don't have a smoking evidence, the smoking gun that you want to see vorticity and gas rotating, okay? I also want to point out another aspect that has not been really mentioned much is that, when you look at these rings, we say they are symmetric, right? But if you look carefully, they are not, at least most of them, they are not really completely symmetric. So symmetric means the intensity does not change in azimuth as you go around the ring, okay? So this is an example of, again, HD 16296, where, this is the image from the sharp. This is what happens if you, what you get if you subtract out the symmetric part of the emission. And if you look at this residual map, clearly there are evidence asymmetries like this crescent that you can also see in the image. But there are other subtle features which are actually real, right? We are always, we always look at the brightest stuff, but if you look beyond the brightest stuff, there are asymmetries like, for example, here, and you can see even in the image that this ring here is not perfectly symmetric. So this is in the polar plot, these asymmetries. There are asymmetries at the level of, 10% or 5% of the peak flux, which are real. So even dust rings are not necessarily perfectly symmetric, and that's also tell us about the evolution of the dust and or the origin of these rings. Okay, the last special class of asymmetries are spiral structures. Okay, these are even more rare, even rarer than general asymmetries. They are only seen in a few objects, although this number is increasing. Oh, sorry, I forgot here the year. This is Paris et al. 2015, Elias 27, and this is from also Jane 1 paper. You have seen all these pictures. We had a very nice talk yesterday about multiplicity and how, for example, S205, the spiral structure in S205 is likely due to the dynamical interaction with the companion. This is not difficult to reproduce in, for example, simulation of the interaction between this object. But for other objects which are single as far as we know, like LS27, IM loopy, and WAO46, the fact that we see this M2 spiral is surprising. M2 spiral can be created by gravitational instabilities or planets maybe, but the large pitch angle of the spiral make it challenging really to compare, to find a model, a good model for this spiral, okay? So I don't have much to say about this spiral except they are really puzzling, okay? So to conclude my description of dust continuum emission, I want to point out that all the observations I show you are single wavelength. And they are great, they are fantastic, but they have also limited amount of information because you don't have information about the spectral index. And the spectral index of the emission can tell you a lot about the composition of this ring in terms of dust properties or also the optical depth. And so far there have not been many studies that really try to complement single wavelength observation across the entire millimeter regime. This is a beautiful example of HL tau by Carrasco Gonzalez, where you have observation from 0.9 millimeter all the way to ALMA and the VLA. I want to stress that VLA is really important to extend the wavelength coverage. However, a VLA has limited sensitivity, and that limit our, the capability of looking at structure at this longer wavelength, and we'll go back to that later. So what you can, once you have this beautiful multi-wavelength observation, you, in particular, if you have more than two, okay, if you have only two, there's not much you can do except measuring a spectral index. But if you have more, you can really try to disentangle your model. So the emission depends on the column density, the temperature, and the dust properties. And so if you have more observation, you can, in a model-independent way, fit for optical depth, temperature, and dust opacity. In the last 5 years, it has been the role of scattering a millimeter wavelength has become more relevant. And so you need to include scattering also in these models. And this is what Carlos did. But no, you get this beautiful, these are essentially intensity profile. You can derive spectral index. You can derive optical depth. And what you find is that the optical depth is pretty large, right? In these rings, so the B21, B4, these are the rings in HL tau. Optical depth at least 1 millimeter can be as high as 8 or 10. And even in the VLA band, the optical depth can be pretty large. If these rings are dust traps, okay, you expect to find large grain at the position of the ring and smaller grain in the gaps. And large grain are traced by beta, where beta is the slope of the dust opacity, and the larger the grain are, the smaller their slope is. So what you expect to see at the position of this bright ring is a drop in beta, which is not necessarily what the observations show. Okay, and this is also relatively puzzling because we don't have, with the caveat that the angular resolution is not fantastic to resolve the structure, and we'll go back again to that later. But we don't really have from this observation, strong support of the idea that there are large grain in the center of the ring compared to the outer part. I want to feature this new result that will come up soon by Greta Guidi and collaborator, including myself, where we collected this set of ALMA observation of HD 16296 multi-wavelength observation. And similarly to HL tau, we don't really find very strong evidence that there are large grains, that the grains in the rings are larger than the grains in the gaps, okay? So that's something that, so stay tuned. I also want to point you to Feng Long talk. So let's move on because time is running fast here. Scattered light emission, structuring scattered light coming from the surface of the disk. There have been many beautiful work analysis done thanks to with Sphere, but also GPI and also Subaru with KXIO. And I want to point you to this talk by Takayuki Uyama. And you can clearly see what I was talking about in terms of scattered light tracing the surface of the disk. I am loopy, for example, also DOR25, where you see the both sides. This allow you to tell what is the near side of the disk, where you see the dark lane. There is asymmetry due to phase scattering effect, scattering phase effect. And it's really interesting to compare scattered light with ALMA observation. And for example, this is I am loopy again. You see a spiral in the millimeter emission, and scattered light is much more optically thick, so only trace the surface. You can kind of see structures. It's really difficult to match structure in scattered light to structure in millimeter wave emission, though, because they trace very different regions of the disk, and also they trace very different grains. Scattered light trace micron-sized particle or sub-micron particle, while millimeter trace millimeter grains. An attempt of comparing scattered light and ALMA images was again recently done by Nienke, Van der Marel, and you can see here, and also by Antonio Garuffi. And you know, there are many things you can take out of this comparison. I want to point, I think the comparison between ALMA and scattered light was nicely summarized by Antonio paper. We say, however, the paucity of spiral and shadow from the sample, where the sample is talking about Titori star, reinforces the trend according to which these near-infrared features are associated with Herbig star, so this spiral feature, either because they are older or more massive. Furthermore, these rings that are apparent in ALMA observation of some target do not appear to have corresponding detection in sphere. So, it's not trivial to compare properly observation at these different wavelengths because they trace so different regions. This is a beautiful example of TW Hydra, scattered light emission here, panel A, millimeter emission, and you can see how different they are. And I want to point out that it's complicated because the comparison is complicated, and this is some model I did with Neil Turner and published in 2018, because if you have structure, because the scattered light is really sensitive to the surface of the disk. If you have bending waves in the surface, as for example caused by gaps in the dust continuum emission, some region of the disk can be illuminated more directly than other. And the more direct illumination results in a higher temperature results in a higher scale light, and the higher scale light results in a higher illumination. So there is this, you can even reach a situation where you are not even stable, right? So this shows, for example, this dark ring you see here in TW Hydra, for example, in scattered light, doesn't necessarily mean you have lack of dust. This can be in the shade of a puffed up ring close to the dust gap. And we see exactly this thing in simulation. I want to point out that whenever you change the surface density of the disk, for example, introducing a gap, because you change the illumination of the disk, you change the temperature of the disk, okay? And so this has important effect, not only on the hydrodynamic structure on the disk and on the dynamic, but also, for example, on the chemistry, because you can move snow line around by changing the illumination of the disk. And the last thing I want to point out as a caveat is that the fact that you see shallow ring in the millimeter wave emission it doesn't necessarily mean that there are rings in the density of the dust. This ring might be caused to temperature variation, okay? So be careful when you say, a 10% ring in the intensity in the millimeter emission. That doesn't necessarily mean that there is a ring in the dust density, okay? Temperature is not radially monotonic once you have gaps and structure in the disk. Okay, let me move to the gas. Okay, this is the elephant in the room, as I said before, that we had beautiful talk by Ilaria Pascucci and Miotello. Gas emission can show very different structure compared to the dust. I'm not gonna review anything about the general, we have seen rings in the gas emission. The only point I want to focus here is whether do we see structure in the gas emission that correspond to structure in the dust emission, okay? So the first question is, do dust cavity correspond to gas cavities? Yes, to some extent. These are a compilation of transitional disks where you see large cavities in the dust. And to some extent, they also show gas cavities. But what we find is that the gas cavity generally are shallower than dust cavities. Okay, this is a case of HD 142527 by paper by Jan Boller, which is shown here. You have this beautiful crescent in the dust, but you see the gas is much more homogeneous. In the position, in the direction of this crescent, this model, if you look at the red lines, you see that the dust is very concentrated radially, the gas is much more spread out. At the position of the peak, we measure high dust to gas ratio, which is another extremely important quantity. Is what is the dust to gas ratio in these structures? Because that really controls the dynamic of dust. I want to point out Mully's talk also. Do we see gaps ring? Do we see gaps in the gas where we see gaps in the dust? And this is much more difficult challenge to resolve. This is from one of my papers, 2016, HD 16096, dust continuum to LCO, 13CO, C18O. What you expect to see are rings in C18O, which is mostly optically thin if there is a gap in the gas. And these are normal intensity profile. There is nothing really obvious here. You don't obviously see any prominent ring. However, when you do the modeling, you find that at the position of the dust gaps, there is evidence of some depletion in gas, okay? And these are complicated models. I want to point out work by Nienke and also the nice talk by Christian Raab, where you can, these are complicated models, and so I think the results are, need to be demonstrated. I want to point out again, gas to dust ratio can be relatively low in the position of these rings. Okay, this is not unity, but is of the order maybe a 1020. Okay, I need to check the time because I don't see the clock anymore. Okay. Okay, more work have been done to look for gas gaps. This is by Fedele, HD 169142. And this is the recent work on HL tau. And in general, these work tend to agree that there is some evidence of depletion of dust in the gas, in the dust rings. Although I think the jury is still out, we need more confirmation for that. Okay, I want to very quickly go to origin. This was already covered by Paula, as you can see in my slide here that I made by stitching together a screenshot from Paula talk. No, I don't want to enter into any of these except that they are all reasonable processes to create structure. This is my synthesis. I think we have three ideas here. You can either have planet forming structure, chemistry, or instabilities. Planets, the pros is that they can naturally reproduce many observed structure. PDS 70 is a poster child for this family where we do see planets and we do see rings. The issues here is that, well, PDS 70 is the only object we have that kind of direct demonstration. And as Alice Zurlo yesterday talk pointed out, is we need to find these planets, okay? I want to open a parenthesis to share some very new result on PDS 70 that was mentioned yesterday, also in the framework of circumplanetary disks. These are the old observation, well, not very old, as you can see from the age, where ALMA observation, we showed detection of emission at the position of the two planets. And these are very new ALMA observations that will be published soon by Miriam Benisty, where we redetect emission from PDS-70C in the millimeter wavelength, very well separated by the disk. Okay, these are completely independent observation compared to the one I showed before. And when you go to lower angular resolution by using a different weighting function, we recover emission around the position of PDS-70B, but this emission is much more diffused, and that's why it goes away when you use a more higher angular resolution. And this may be connected to the disk. So stay tuned. There are also new, very interesting results on PDS-70 from Miriam Kepler, where we have a detailed analysis of the 12CO emission. Okay, chemistry. Chemistry can be the structure produced by chemistry. Yes, why not? You know, chemistry is important. However, I'm not completely convinced that the model we have so far can really reproduce the observation. And when I say that, I mean, you know, how do you reproduce asymmetries? How do you reproduce the number, the variety, and the position of the rings? How do you reproduce velocity variation, like the one, for example, described by Christophe Pant? So I think, you know, my main issue here is chemistry is important, but I'm not sure it's the most relevant phenomenon. And I want to point out that if you think that rings are created as no lines, we really don't see any evidence that the position of the ring agreeing with the position of snow line. Okay. A few more slides, although I think I'm running out of time, but so I'll try to get to the end. Instabilities. Yes, I mean, instabilities, why not? Nature is very unstable. And, you know, the problem with instability is that they tend to be difficult to study because you need all the physics in your model. And again, I'm not sure you can reproduce grand design structure like the big rings we see or the M2 spiral. This was already shown in the previous talk. So, you know, one thing we should also think about is, are the structure the result of initial condition of or evolution? Okay. You know, I don't want to spend more time than what has been already done here. I think this is a reasonable idea, but there are a lot of issues. You know, we are looking at limited sample. The opacity of this young object, class 0-1 object, is very high. So the fact that you don't see a structure, it doesn't mean they are not there. Maybe just you are completely optically thick. Initial condition is something interesting. We have increasing evidence of these objects accrete material from their own envelope through streamers. I wonder if this asymmetric accretion can lead, for example, to ring structure in the disk. So maybe that's something for the discussion. Okay, so what are the open questions for the future? This takes me to the end. I think we need to increase the angular resolution. We want to detect structure in the terrestrial prime farming region. Okay, in the next few years, we will reach the limit of ALMA capabilities. On top of that, there is an optical depth problem that these regions tend to be optically thick. So I think that really the workaround is to have, you know, an interferometer that works at longer wavelength, and the NGVLA is really key to do that, because you have 10 times the ALMA sensitivity at 3 millimeter, 10 times the angular resolution, and really you can map this innermost region in much higher precision. This is a simulation by Luca Ricci. And you know, this is a Jupiter, this is a young Jupiter with, you know, Trojan satellites. And I think the key is that when you go to such small orbital radii, 5 astronomical units or less, you open up a completely new windows, which is the time, right? The orbital time scale is much, much shorter. You know? It takes 11 years for Jupiter to orbit the sun. And so you can go back and really not only take this picture once, but you can see how these things move around. And this would be fantastic and really revolutionary. We need to detect planets, okay? That's what Alice Zurlo pointed out yesterday. I want to point out that JWST has the capability to detect at least some of these planets. So this is a shameless advertisement of a JWST proposal submitted by Luca Ricci, where we try to detect directly some of the planet might cause the ring in HD 163-96. So this is possible to some extent, okay? Although, you know, JWST, the angular resolution is not fantastic, but the fact that you look in the thermal emission where these planets are supposed to be the brightest really helps you a lot. Another open question is, we want to resolve the structure within the structure, right? This is a paper in preparation by myself, MWC 758. If you zoom in the structure, they appear to be clumpy, but are this clump real? It's very difficult to tell whether this clump is real or not. We have simulation that suggests that when you have high dust to gas ratio, there are dust instabilities that could lead to clumps, even before the onset of streaming instabilities. This is a paper by Pingui 1, where we show the existence of mesoscale instabilities that can break up the rings in clumps. And then in these clumps, you can have streaming instability kicking in, right? And we want to resolve this structure and see if they are clumpy or not. And last but not least, again, the elephant in the room is the gas. So we really need to get higher resolution in molecular line emission. It takes a lot of time. It takes a lot of ALMA time. This is a recent result by Facchini for PDS 70, a lot of line emission. You can do a lot of chemistry, but as you can see, the angular resolution in the continuum is still very different from the angular resolution in the line emission. Mapping line at high angular resolution is not impossible. This MWC 750 AC18 2-to-1 line map at 80 milliarc-second resolution. You can see there is signal, but it takes a lot of ALMA time. So I think we need to be, also the panel, the review panel need to be open to the idea of locating many, many hours of time to this project. Okay, I'm late, so I'm gonna finish here with my Christmas wish list, because we are close to Christmas. My first wish for Christmas, for Santa, is please bring ALMA back. Okay, so we have had this fantastic conference, and ALMA has been offline for a long time. I know I want to thank all the people, all the ALMA staff that is doing a huge amount of work trying to bring ALMA back. It's a daunting job to bring back a telescope like ALMA after many, many months of shutdown. So, but I hope that in the spring of 2021, we could go back to get new ALMA data. My second wish is give us a lot of ALMA time to measure the density and velocity of gas across dust ring and asymmetries. We need to increase the sample. We need to get better angular resolution. We need to get better sensitivity in the line emission. My third wish is give us a lot of ALMA time to study small scale property of our ring asymmetry. I think we really would like to zoom in and see whether the structure we see, we detected them. Now we want to zoom in, resolve them, and see whether they have substructure in them. Give us some JWST time to detect planets in dust gaps. This will really, if we could show that if we could detect these gaps, this will really provide a direct connection with the exoplanet field and all the stuff that Didier Queloz have talked about on Monday. And my last wish is please give us the NGVLA, because I think that's really a natural evolution of ALMA. We can look at the much younger objects where the optical depth is an issue. We can have much better angular resolution. I would like to say that the NGVLA is still a design, and if you want to contribute to developing this design science cases, please get in touch with me. And with that, I would like to apologize for being late, and I would like to wish you a Merry Christmas. So I stop here. I'll be happy to take any question.
Thank you, Andrea. That was an excellent talk and a very long wish list, but I'm sure a lot of us have a very similar one. Okay, so we have a lot of questions. So the first one you kind of addressed a little bit at the end of your talk. It's kind of the chicken and egg question. So how do you form the first planets before rings are formed?
Yeah, that's a good question. And I have my own, okay, I don't have any data to support my idea, but I think it's reasonable to think that planets formation might not occur only in one way, right? So it's possible that core accretion is the way you form rocket planets, and in the way you form planetesimal in these rings. But in a very early phase, like the beautiful observation that Patrick showed, these around class 0 and class 1 stars are much more massive, are more compact, And so that means that there might be more gravitationally unstable, particularly the dust layer. So when dust settles on the midplane can become more unstable. So you don't need to have the entire disk to be unstable. You can have a midplane that is unstable, it can collapse. So I mean, my really personal impression is that there may be an early phase where you form, you know, giant planet through some combination of gravitational and dust instabilities. They create structures, and in this structure you can form second generation of rocky planets. And for example, the implication, we have some evidence that in the solar system, well, first of all, Jupiter formed before Earth, okay, but you need Jupiter really to open a gap in the disk to explain a lot of the characteristic of geochemistry and in meteorites. And so I think we are getting to the point where maybe giant planets have a very important role in forming rocky planets, much more important than what we thought in the past.
Yeah, that actually answers the other question on the list. So actually, if gaps are caused by planets, then we expect a second generation of planet formation in the rings, right?
Yeah, so I mean, this is a question for the theoretician, and there have been a lot of works. I mean, my review really focused on observation because there was too much theoretical work done to be able to put everything together. But there has been a lot of work that show clearly once you, when you trap dust in these rings, and when your dust to gas ratio increases and it can reach unity, then you really have a lot of dust instabilities like the one I show you. And then you can form planetesimal. I think there are works that suggest streaming instability can both be enhanced and quenched depending on the specific details of the model, but there is no doubt that you can trap a lot of dust in these rings. And that's overcome a really old problem of, how do you know if you spread your dust out across the entire disk, the column density for the masses we estimate is generally low, okay? But now if you put the same mass, total mass, then you put it all in a narrow ring, then your density increases a lot, and that helps a lot the formation of planetesimals.
So regarding the asymmetries, and also related to the talk by Patrick, so how early do we expect to see vortices in disks? Could they also be present in younger class 0 objects, for example?
Yeah, it's a good question. Well, first of all, I would like to make sure they are vortices. As I said, we still don't have the smoking gun that these are vortices. Vortices, you need the low viscosity to trigger these instabilities, because if the viscosity is large, well, at least, if you think of viscosity in terms of an alpha disk, which might not be the proper way to think to viscosity, but if you have high viscosity, the viscosity tend to kill most of the instabilities. So if you have low viscosity, whenever you form a gap whenever you have a discontinuity in the surface density, a discontinuity in the velocity, in the orbital velocity, or in the viscosity itself, you can trigger Rossby wave instabilities, which tend to give you vortices. And there are a number of simulations that show you may start with many, many small vortices. A lot of modeled by Balboro, and these vortices can join in larger vortices. So how early, I don't know, but I mean, as soon as you form this structure, you may form vortices in the limit that your viscosity must be low. And I want to point out something that I mentioned, that the fact we see this extremely narrow ring in some system like AS209 really suggests me that there is not much turbulence that can broad up this ring. So at least in this region, I think we have some evidence that viscosity is pretty low.
Yeah, so actually we have a Jehan Bey on Slack. He's saying that vortices can form as early as when the envelope material arrives the disk during the infill phase, and also during the late infill.
Thank you. Yes. Yeah, I'm not the best person to answer the question. Jane is.
Okay, there's another question by Eric Jensen. So do we see rings that are still unresolved by the highest angular resolution ALMA observation? So for example, are the rings in AS209s the narrowest rings that we have found so far, or there are other examples?
Yeah, I think the answer is why this? Okay, I think the answer is yes. We see structures that are not resolved, and also, you know, there is a technical point, but the fact that we see, you know, is a bit a technical point. You know, we generally assume that ALMA observations are not affected by seeing as optical observation are, right? So if you see something that is bigger than the beam, you say, well, I resolved, this is resolved. Well, it's not necessarily true, although, you know, we do self-calibration and all the other techniques that allow us to reduce decorrelation. There is still some decorrelation in the data, right? Which means that, you know, even if you have a perfectly point source, it's going to be slightly larger than the beam if you don't calibrate your data properly. So for you can see here, for example, HD 143006, you know, this ring is pretty much unresolved, okay? You know, and other disk, so this sigma B, so this green line is the resolution of the observation, okay, essentially. So the fact that these rings are so close to the green line is telling you that, you know, they could be unresolved, or if there is some residual decorrelation in the data. So by the way, S209, ring 1 and ring 2 are here. You see how close they are to the, you know, this is the, if you like, theoretical maximum resolution.
Yeah. Another question. So how should we interpret the high optical depth of millimeter wavelengths in the gaps of HL tau?
Yes, that's actually a very good question, and that's a question for Carlos, because I had the same question myself. So let me go there. And I was puzzled. Well, actually, I think I might have the answer, and unfortunately, it's not shown here. So in the gap DHL tau, the optical depth is still very large, but we see the gaps, right? So which means that it's really not, well, you know, there is some effect of dust depletion, but the main effect is temperature. So I think what's going on here is that the temperature in the gaps is lower than the temperature in the ring, and that temperature effect is what produces some of the contrast in the ring, right? Because at 0.9 millimeter, we clearly see the gaps. But now, you know, the optical depth is in the gap is 6. So how do you reconcile this? And for me, the only way you reconcile this is by changing the temperature, which I think is another figure that I didn't show here. And it goes back to the point I made that, you know, if you have a model where, you know, we always assume that the temperature in the mid-plane scale as the 1 over the square root of the radius, right? That's true if you have a smooth disk, right? If you carve gap in the disk, and if you carve gaps also in the millimeter particles, you know, you change how the disk is illuminated. And if for these class 2 disks where most of, well, it might not be the case for HL tau, but class 2 disk or class 1 disk where you are far away from the star, if most of the heating comes from the star itself and not viscous accretion, changing the illumination of the disk really changes the temperature. If you have viscous accretion, then, you know, viscosity, the viscous accretion, viscous heating depends on the viscosity. So if you have if your alpha changes with radius, viscous heating will also change. So, you know, it goes back to my caveat that be careful when you see shallow structure in the dust, in the dust emission, to call them as a result of dust density, because temperature variation are not negligible or might not be negligible. But I would like to hear from Carlos about how he actually reconcile the high optical depth to the rings.
Yeah, okay, so we don't have much time, but if I can just ask one more question, that is actually a discussion that is was going on Slack about observations at longer wavelengths. So what do you think is going to be the main, so what are you looking forward from these NGVLA observations, for example, and what are the caveats that we will have there?
So the easy way to see it now, this is what VLA give you now. Okay, this is HD 16396, and you can see the staggering difference between 8 millimeter and 0.8 millimeter. Clearly the VLA, unfortunately, it just doesn't have the sensitivity. The angular resolution is not that bad. You can get something like 70, 80 milliarc second. It doesn't really match the ALMA resolution, but it's not that bad. But the sensitivity is what really kills you. So, if we want to understand dust trapping, whether dust trapping is actually real or not, happening or not is real, whether it's happening or not, and also resolve and see clumpy structure in this ring, which are optically thick, as we already discussed, we really need to go to longer wavelength. So the NGVLA will give you something like the ALMA images, but at 1 centimeter, right? So take the image 1.3 millimeter, see what you see now. If we can build the NGVLA, you would get something similar to what you see now to 1.3 millimeter, all the way to 1 centimeter. With, depending on the source, in theory, you can go down to angular resolution as small as a few milliarc second, maybe 1 to 5 milliarc second. Clearly, if you go to this high angular resolution, you need to have extremely bright source to be able to resolve them. But I'm not saying we're going to get 1 milliarc second observation of disk with NGVLA, but for sure we could get down to 5 milliarc second or 10 milliarc second. But it's really the sensitivity that really is going to be what improves. I want to point out that there's going to be an ALMA band 1, right? ALMA band 1 is going to give us observation at 7 millimeter. But if you look at the details, the sensitivity of ALMA band 1 is comparable to the sensitivity of the VLA, with a much better UV coverage, much better image quality. But sensitivity-wise, I'm not sure that ALMA band 1 will give us, image. By the way, ALMA band 1 also the angular resolution will be much worse than at 1 millimeter, for example.
Okay. Thank you so much, Andrea, for this wonderful talk and for all the questions. There were many questions left in Slido, so they will post them on Slack, so you want to...
I'll do my best to go through them.
Yes, thank you. So I think we have a 30-minute break right now. I don't know if, Alvaro, you want to give any announcements?
Yeah, no, that's right. Thank you very much, Viviana, for chairing the session. Thank you, Patrick and Andrea, for your great talks today. We're going to go into a break now. We'll leave you guys with a poll, and we'll come back at 30 past the hour. See you. welcome back, everyone. Before we go to the discussion, let's take a look at this. I think I'm going to eloquently avoid to discuss this because whatever I say, I'm going to make a lot of people angry. And also, well, yeah, I was thinking maybe we chose the name of the conference wrong, but 5 years after HD 1632-96 would sound a bit weird. So yeah, we're going to move on to the discussion session today. That will be moderated by Nienke van den Marel and Sean Andrews. I just want to point out that they have quite a few polls, so make sure to change the Slido room to the corresponding one for the discussion session. And with that, okay, Sean, it's all yours.
Sorry, now you can unmute yourselves.
Thank you. Thank you. Yeah, hi everyone. I'm so excited about this discussion. I'm really curious what we're gonna see in the answers to all of our polls. Yeah, so as Alvaro already mentioned, we have 13 poll questions and the panelists have already seen them. And the way that this is gonna work is we're gonna show the poll in Slido. The audience will have maybe 10-20 seconds to vote, so please don't wait too long because we want to get the discussion started. And then for each poll question, we will point to one of the panelists. Again, they are aware of this, who will start the discussion. And after that, everyone on the panel can chime in. Of course, just like Wednesday, feel free to have discussions and comments on the Slack. We will try to keep track of everything where we can and merge everything together. So yeah, let's get started.
Okay, can we have the first poll question up, or is it up? Right, so we've discussed this quite a lot already in the conference, but now that the talks are ended and we're sort of summarizing what's going on, we just wanted to see what people think is the most relevant mechanism for creating substructures. Obviously, multiple things could be happening, but that's why the word most relevant came in. And we're gonna, I was gonna make Paula chime in here, but since her voice is still recovering, we'll have Mario Flock get us off. But I did want to sort of, obviously this isn't just Mario or whoever, their opinion. I did want to sort of focus the conversation to think about what would be a convincing case or piece of evidence for these mechanisms, and do we already have it? Obviously, so planet disk interactions, it's pretty easy to say a convincing case if you find a planet. But the other ones are sort of less obvious, so I'm sort of curious to hear what people say. So maybe Mario can start us off, and panelists, if you want to chime in, please do raise your hand in Zoom.
Yeah, thanks, Sean. Thanks, Nienke. So, yeah, as you mentioned, I think it's very difficult, right? So when we look at the dust continuum, I think we all agree that it's very difficult to let's say understand the mechanism, what causes these structures in the dust continuum. But I think now with the upcoming observations of the kinematics, of the CO kinematics, I think that is a way to go, so to really identify what we are looking at. So, and then I would actually pass on to Christoph Pant or to Richard Teague. So I wonder, if we are already at a stage where we can really say, from the kinematics, this is really, that this has to be a planet just because of, the velocity and the point source, or if it is more difficult because we are looking at the surface and we cannot really see, the dynamics at the midplane. So I wonder, what is your take on that?
At least that in a few cases like HD163, HD97, the signature is mimics so well what we find in a model for a planet that it's a very strong argument. When you run a model, you just put a planet inside, you get a king that looks exactly like in the observation. And so far, we haven't come up with another explanation that could explain both the gap and the kinematic signature with a localized signature and velocity. So I think those two detections at least are very robust, and it would be very difficult to explain them without a planet.
Yes, I see. But I guess this would apply only for, let's say, very massive planets, if I'm right? So
yeah. So in both cases, we find planets of a few Jupiter masses. And of course, the key question is that if you have a Neptune mass or something like that, what would be the signature and how we can distinguish from other mechanisms that will be important when you reach low velocities. So, and I don't think we have that answer yet, but hopefully in the next few years, we'll be able to find ways to look at the data and be able to distinguish between low-ish mass planet and other mechanisms.
Thanks.
And I think we'll get back to some details about this in a separate poll. But Rich, did you want to weigh in as well?
Yeah, I just think that at the moment, the observations that we have are really good for the outer disk in terms of the gas kinematics. To really push into the regions where we're exploring, say, the rings that we see in D#, we really need to go back and get targeted observations for these sort of things. The spatial resolutions just aren't being achieved at the sensitivities that we need to really detect the subtle perturbations that you'd expect for a planet. So that's going to be the real big challenge in the next few years.
So we're pretty focused on the planets, as the poll said, but I do want, I mean, the reason I picked on you, Mario, is because I do want someone to weigh in on how could we, instead of the logic of negation here, how could we rule in some of these other mechanisms? Is there some hope for that, or should we just all wait till we detect the planets and just bail?
Well, yeah, my point on that is, to look at the kinematics, because once we know, kinematical structures, so when we know really the velocities, then we can start and compare by, hydrodynamical models, by magnetohydrodynamical models. So I think that's the way to go, right? By just looking at the dust continuum, that's not possible, because just too many effects can cause these structures in the dust continuum. So I think really the way to go is the kinematics. At the moment, I don't see any other good, let's say, way to do that. So that would be my take on it.
Yeah, I just want to add to that I totally agree with Mario, and I think on top of that, we need to see how deep are these gaps in gas too, if they exist in gas, because this can also help us to exclude some mechanisms, like we don't expect the snow lines, for instance, to create deep gaps in the gas, more just to have an effect only in the dust. So this really will help us to see or to exclude some mechanisms.
Anyone else want to weigh in before we move to the next poll? Leslie.
Yeah.
I just have to put in a dish for what Patrick was talking about, which is effectively looking at the evolutionary pattern of these substructures, and particularly going back to the younger sources, where we're beginning to see that there's at least hints of them in prevalence and very interesting variation, of course. So as we get more higher resolution imaging of the younger sources, these class 0, class 1s, I think that's also going to elucidate some of the structure. At least I hope so.
Well, I have a question here in terms of, because Mario points out that we really need to measure the kinematics to look at these other scenarios. But how confident are we that we will be able to do this for a large number of disks, or will this only be possible for the handful of brightest disks? What are the predictions there from the theorists?
Good question. Yeah. Somebody can jump in here.
Well, I think if I could, as I said before, if you want to have you need to get good measurement of the velocity, you need high spectral resolution and you need high angular resolution, right? So, it is doable, but, it really takes tens of hours of ALMA. And so, so you need to convince review panels that it's worth spending a lot of time to a single object. And I think it will be easier to do that in the future when the pressure for ALMA time will drop maybe a little bit. But that's what you need, right? So you need, and unless the ALMA sensitivity in molecular line is going to increase, which is a possibility with future upgrades. But the current state of the array, you need tens of hours to, if you want to resolve. A question for you, Mario, is what velocity resolution do you need? I mean, to how much do you need to resolve the sound speed to be able to constrain some of these MHD or HD models?
So in Marcello's work, so we found that we need around 5% of the sound speed to resolve. So the VSI produces, velocities in the orders of 50 meters per second. So if we resolve this velocity, then we are able to distinguish, clearly, okay, this could be like, vertical shear instability driven kinematics or something else. So this is also consistent with let's say MHD models, so with magnetorotational instability. So you expect here to have 100 meters per second. But to be on the sure side, I think in the order of 50 meters per second, that's what we would need to really say what's going on here.
50 meters per second is not 5% of the sound speed.
Well, in the regions what we are looked at, what was it, the typical, HOR of 0.1 and 100 AU, we calculated around 50 meters per second. So, but you're right. I mean, more important is the let's say sound speed, and it's around 5 to 10% of the sound speed. So that depends then, where you look, but 5 to 10% of the sound speed, that's what we need.
Yeah. Okay. I
think thank you. Yeah.
I do like Andrea's strange optimism that the ALMA time pressure will go down. I'll take that bet.
Okay, so indeed, it is time to move to the next question, but thanks for the input so far. So the next question, is it already up on the Slido? This is kind of related. So under the assumption that indeed these substructures are all caused by planets, how confident are we that these planets have already formed by the class 2 stage and are indeed perturbing the disk? So this is more about the moment in time that these substructures are being created. So let's see how the audience feels about it. Looks pretty confident so far. 1% of people doesn't buy it. No, but the overall trend looks like that everyone is, most people are pretty convinced of this. So, Jehan, would you like to comment on this high confidence level?
Oh yeah, sure. First of all, I chose 70 to 90, so I'm glad to see many of us agree with my opinion. But I should say that I tweaked the question a little bit before I answered, because it can be basically anywhere between 0 to 100, depending on exactly what you are trying to answer, right? So what I answered is that if we have to form a planet, right, here's a big if, right, where planet here means that gas or ice giants in the outer disk beyond about 10 AU, where we are most sensitive with imaging, right? It has to happen already before class 2, right? And this is because I think the majority of class 2 disks are not sufficiently massive to trigger GI at the moment, although it is not completely impossible if we consider late accretion, for example. And also the other part of this is that if we already seen this in Patrick's talk today and Ilaria's talk earlier this week, but the dust mass available in class 2 phase seems to be not enough to form a new core of a giant planet. Most of them has less than 10 Earth masses or so. So I think for those 2 reasons, I think it has to happen already in class 2.
You mean before class 2?
Yeah, before class 2.
Okay. Yeah, who wants to chime in on that? I see Giuseppe has unmuted himself.
Yeah, I think it depends, as Jehan was saying, on what do we define as planets. Obviously, it's different if we talk about Jupiter mass planets or lower mass planets. So it depends on that. And also, I think it does depend on all other parameters that go in, stellar mass, environment, etc. So I think for the planets that we think we are seeing, for example, in gaps or in the kinematics, I agree it has to happen early on. It's not obvious that this is the same for any kind of planet or any kind of planet of stellar mass, etc.
Okay. Don't see any raised hands at this point. Maybe Kate would like to say something? Yeah.
I was just going to add to what Jayon said that I think the ubiquity of substructures and the variety of substructures that we observe in class 2 disks suggests that, you know, I guess for any given substructure, there are alternative hypotheses for how you can generate it, but planet formation is kind of in the list or the favored hypothesis for most of them, right? And so if you look, for example, at cavities, you know, the degrees to which they're cleared and their sizes, they certainly can't all be explained by the alternative mechanisms like photoevaporation. And so I think there's a bit of a chicken and egg problem with all of this discussion of whether substructures are planet induced or planet forming. But
we'll come back to that in a
right. But I think that the most compelling thing, and I'm not a millimeter observer, is that if we are getting our disk masses right, then they kind of have to form by the class 2 phase in order to reproduce the statistics from radial velocity and transit surveys.
Maybe someone from the early, who's working on the early disks would like to say something. Patrick?
Sure, I can jump in a little bit. I mean, I think to some degree, some amount, maybe my answer would be that some amount of planets have to have formed for, I think, all of the arguments that have been put out. But I also don't know if I'd say it's the end of planet formation and that more planets might yet still form. But it certainly seems like with substructures being present sort of everywhere in the class 2 disks, that something needs to have formed sort of early on, is my take on it.
Right. So yeah, I think a lot of this is now about the details of what is really happening during that early phase. So why don't we move to the next poll question? And Sean can take over.
All right. So the next poll question is basically what we've already started to talk about, is just trying to pinpoint if planets are actually responsible for substructures. When do we think that most of the planets are forming? We give a bunch of options, including the option to stop talking about planets. I'm very curious about the results here. I don't have my own opinion, really. Well, there's a lot of entries already that are arguing sort of for at the end of envelope, or late in envelope dissipation, so class 1 phase. Let's start the conversation with Dominique.
Yeah, so I think this sort of relates back to what we were just talking about, and I think it depends on what you mean by planet. So if we're talking about something that's small enough that it's not yet triggering runaway accretion of the gas, so something less than 10 Earth masses, maybe that's still enough to start to carve out the gaps that we see. But if we start doing that too early, for instance, in the class 0 phase, I wonder how we're going to stop this gas accretion process. So are we then going to trigger like brown dwarf formation or binary formation? But if we do it later in the class 1 phase, maybe that's enough time to gather enough mass into a planet so it can carve out the nice gaps for the class 2 phase, but then not actually form the brown dwarfs, because we don't see brown dwarfs in the D-sharp disks. So that's sort of my idea and my vote for the class 1 phase.
Yeah, that's an excellent point. The timescales and starting and stopping is a big issue. We'll come back to that a little bit later, but that's an interesting point. Who else wants to weigh in? Someone else working on these young sources. We have plenty of you. Patrick, go ahead.
Yeah, I guess I can say that I think the process probably starts early on, but you know, certainly we see potentially even some evidence that going from the class 0 to class 1s, that disk masses might be decreasing, which could be some amount of indication of evolution. But on the other hand, it's going to take some amount of time to get to the point where you actually have something that could carve a gap. So while I think the process probably starts close to the beginning, I guess the question is, when does the planet actually show up? And that probably, but maybe some theorists could correct me if I'm wrong, would probably take more than the class 0 timescale.
Let's see, Leslie has his hand up.
I think I just want to echo what Patrick said. I think that's what you actually start as defining as the beginning of the planet formation process, I think probably does initially begin in the class 0 stage. And that's where we're seeing differences in evolution in the Van Dam survey, for example. So I really do think that the initial conditions are beginning to be set at that first stage.
Thanks. I'm curious actually to hear about the accretion, you know, what happens in the accretion process. I wonder, I don't want to put pressure on someone to talk, but I wonder what Meryl thinks about accreting atmospheres and stuff during the class 1 phase, if you're willing.
Yeah, I'm not sure if I have a lot to add to whatever has already been said. And I think I agree with timescales, and that we really need to look at that. And we need, I think, to see for the gas, I don't think we have many very high resolution observations yet of the structure of the gas that we now have for class 2 disks. And I think those would be really important to have as well.
Yeah, that's a really excellent point. I think we're behind on that for the younger sources. It's hard, of course, but right.
We need ALMA to give us a lot of time to look at faint isotopologues and.
Yeah, I mean, to be fair, there are some programs that are doing spectral line observations of these younger systems now. Maybe it'll become clearer once their results are really disseminated. But Daniel, you have your hand up.
I just really liked Andrea's comment that maybe the observations are pushing us towards sort of gravitational instability or something in the dust. And also that, I mean, part of my thinking has been maybe we just get a conveyor belt of planets. Maybe planet formation is basically continuous until you run out of material. That, you know, we know that planets end up in stars, so maybe some of these planets you see early don't survive. Maybe the ones later do. Discuss.
So I might, oh, sorry, go ahead.
I don't even know who's talking, but Jake, go ahead. Was that you? No, who was talking?
Sorry, I was talking.
Okay.
I was going to say, actually, to the point of gravitational instability, though, one thing that's interesting, at least in the Van Dam survey, is that it's not necessarily clear that, say, class 0 or class 1 disks are just, you know, wildly gravitationally unstable in all cases either. So I wouldn't say it's obvious that gravitational instability can work. I mean, there's a lot of questions about what the dust mass actually is, but it's not necessarily obvious that even at the young stages, gravitational instability is very viable.
Yes, a good point. Dominique?
Yeah, so I just want to make a comment sort of on this sort of conveyor belt idea. So what would be really interesting to me that could sort of help solve the chicken egg problem of how are we getting the first planets? Okay, if they're not coming from the first gravitational instabilities, but instead they're coming from a first generation of rings. So what if the embedded phases, there could be rings that are formed by like the MHD winds or secular gravitational instabilities or snow lines or some of these other effects. And we've seen that some of these things might not be very correlated in the class 2 phase, and in the class 2 phase, that's more explained by planets. But if in the class 0 and 1 phases, you have these effects at play, they make the first rings, the rings can make the first planets, and then maybe those first planets can trigger, well, they can reform the rings into the sharp ones we see in D sharp and then make more planets later. So that's sort of one solution, one idea I had for a solution for solving the chicken and egg problem.
Can I ask something to Patrick? Based on what do you say that there is no evidence that disks are wildly gravitationally unstable in early phases?
You can do I mean, it depends a lot of assumptions, but you can do some back of the envelope calculations from the disk masses that you get.
So it's basically, yeah, an estimate of the disk masses, basically.
Yeah, basically, and size and disk masses and sizes.
Okay, but these are very. I mean, there are lots of assumptions, as you say. It's very uncertain how you measure the disk mass.
Yeah, for sure. So there's definitely some uncertainties there, but you have to. I mean, you'd have to increase the masses by quite a bit, which maybe isn't improbable, but what we currently know, I wouldn't say it's obvious that these things are unstable.
Let's move. We're sort of heading to the next question, poll question. So let's shift. And I see some of you with your hands raised, but you're going to be called on shortly anyways. So let's move to the next question.
Yeah, so the next question is indeed connected to this idea that Dominique was just phrasing. A lot of discussion circles around the question of how planets can create dust traps when dust traps are required to form planets. So how can we solve the chicken and egg problem? And we'll be post-still voting this one. Let's wait till a few more answers are coming in. Yeah, and Sean reminds everyone, please raise your hand if you want to say something. Everyone is allowed to speak, of course, after the first comment. So feel free to let us know you want to talk. Okay, so yeah, it looks like the most popular answer is that instabilities leading to dust traps in the embedded phase can be the start of planet formation. And Jeff Gonzalez, what do you think about that?
Okay. First, I'm surprised that the most voted answer is not the gravitational instability, because, well, I think that at least in some cases, especially to explain later on the planets with large separations and very massive that are observed, it seems to be a possible explanation. I'm not convinced that it is an explanation that it's universal by far, but it could happen in some cases. Now coming to instabilities, of course, the streaming instability is a very popular mechanism, and that's one of the different instabilities that can occur and form dust traps that can lead then to planets. But these instabilities were mostly studied in a disk geometry. I'm not sure if anybody has ever tried to study those instabilities in a disk with an envelope or in a much earlier phase. That would be very interesting. And I would actually say the same for all the other possibilities like snow lines or surface dust traps or magnetic field effects. How dependent on the disk phase or the disk geometry are they? That's also something that's important, I think.
Yeah, that's a good point. So Joanna has had her hand raised for a while. So please, Joanna, go ahead.
Yeah, thanks. So yeah, so there is a lot of threads happening here, and I think I would like to just organize a little bit. So, so the streaming instability doesn't just happen. Okay, I think that's the most important point that I want to make, because people say like streaming instability like something obvious, but from all the models that we have been doing is you need something else to trigger streaming instability then. And like in my very biased opinion, this something else, and especially in the very early stage, may actually be the snow lines. And like the fact that the snow lines don't correlate like with the substructures that we see in class 2 disk, that doesn't exclude them, right? Because if you first form a first planet at the snow line, this planet then will trigger like next ring, for example, right? And like the position of this next ring then it's not really the snow line. And like of course, that on top of all the other uncertainties that we have with the temperature in the disk and so on. But like in general, I think this global scenario that Dominique was explaining, that you need to trigger something in the very early stages, like in class 0, class 1, and then this can then help forming next planet. And the substructure that we observe is effect of this like sequential process. This makes a lot of sense to me.
Okay, thank you. I think Paula would like to chime in on that.
Yes, I actually totally agree with Jean-Francois and Joanna in both aspects. We have been focused on doing models of disk and neglecting the effect of the envelope or the cloud. And I think we need to move towards that direction to really answer this question. I briefly mentioned the hydro simulations by Jeff Lesoir that takes into account the infall from an envelope and show that you can have kind of ring or spiral structures. And I think this is only gas models, but there is a lot to see what happens with the dust and if these structures trap the grains and then maybe trigger the streaming instability. And yeah, we are also learning that the streaming instability is easier to trigger than what we thought before. So I think this must be all coming in one single models in the future.
Jake, you've had your hand raised.
Yeah. I just want to sort of put my vote for MHD zonal flows, not only because I worked on them, but because they're a pretty robust thing, and they seem to show up in any variety of MHD calculations, both local and global. No matter what you sort of non-ideal physics you throw at them, they're always there. So it's hard for me to imagine they wouldn't be there in some context, assuming that there are magnetic fields controlling the dynamics of these disks, which is probably pretty reasonable. That's not to say these other mechanisms don't come into play, and it's still, I think it's now the theorists' task to try to figure out how all these various effects, infall, MHD, self-gravity, all these things might talk to each other. But the robustness of MHD zonal flows gives me hope that that might be a route, right, to produce these substructures in the very earliest systems.
Okay, Giuseppe?
Doesn't the
please,
sorry?
Never mind.
I was going to ask, doesn't the streaming instability require a fairly large dust-to-dust ratio? And how much is this likely in the earliest phases of the lifetime of a disk?
The dust-to-gas ratio that's required depends on the particle size. But it's less than 10%. I mean, so it's somewhere between 1% and 10%, depending on the particle size, which is kind of a huge range. But for reasonable particle sizes, 4 or 5% is probably a reasonable number.
I think 2% is kind of the.
Yeah, but 2% is more for like for the Stokes number of 0.1 or 1. That's less likely to be the case, especially in these earlier disks that are probably more massive and so have more gas. The Stokes numbers will be lower.
Andrea?
Yeah, I mean, I want to make a comment that the fact that we need to form structure from a smooth disk to start with is a pretty weak assumption. I mean, why disk must form smooth and then we need to make structure in them? It comes from a very simplified model of accretion, formation of disk, and the fact that disk evolve viscously so that you smooth out any structure. But observation of young stars show us that accretion happens in a very non-symmetric way. So I wonder whether maybe you form disk with structure and you don't need to form them out of a smooth disk through some instability. So, and I haven't seen much of that work done, right? HL-tau itself is a streamer, IRS-63 is a streamer. We see spiral in many class 2 disk even. So why do you need to form structure after you form a smooth disk? I'm not sure we have a good answer for that.
Right. So with that, I think we're going to move to the next poll, because another question that we haven't really discussed yet is how, if things are related to planets, if substructures are linked to planets, how do we make those planets at these very large distances from the star? And sorry, I need to hand over to Sean.
Yeah, I mean, this is sort of the question that I personally always like to just not worry about. But it's sort of timely to start thinking about this, right? Like the classical picture of core accretion and even the updates from pebble accretion, it's not entirely obvious that we could make planets in a reasonable time scale to be consistent with the substructures, if that's what they're actually forming. I see there's a lot of interest in gravitational instability, and we're going to start with Giuseppe, who can tell us if that actually makes sense or not. So why don't you go ahead?
So actually, I'm quite surprised of this poll because I think 10 years ago nobody would bet on gravitational instabilities. Well, now it's the apparently the preferred answer from everyone. So it's quite interesting. I didn't vote for gravitational instability myself. I voted for some hybrid scenario. I think. Clearly, the reason why I think gravitational instability is taking place in the community is because, obviously, it's not just how do we make planets of 50 to hundreds of AU, but how do we make them in less than a million years? That's really where the core accretion probably is having a lot of difficulties. And at the same time, I think gravitational instability might work. Certainly works, but I'm not sure that it provides planets of the correct mass. Usually the planet masses, the fragment masses that we get out of gravitational instabilities are relatively high, are more like several to tens of Jupiter masses rather than a few Jupiter masses. So it will certainly make some fragments, some low mass companions, some binaries, but I think it's, if we're speaking about a few Jupiter masses, then I think it's a bit harder. What I would prefer is, as I said, some hybrid scenario. What I think could happen is that the disks are gravitationally unstable in the earliest phases. They produce structures like spiral structures that are a very effective way of collecting solids in the spiral and kickstarting the planet formation process by producing large planetesimals or even planetary core already very early on in the evolution of the disk. Here, however, I think the big questions that remain unanswered are how massive would this solid fragment be in these early phases, and how much gas mass can they accrete? So I think these two are the questions that we still need to answer from a theory point of view in this. But I guess this hybrid scenario where you have some gravitational instability, the TACS as a promoter of the solid collection and the formation of cores is the way to go. We've done some work about this in the early 2000s with Ken Rice, but I think this has not been followed up a lot. But I think the evidence that is accumulating in this recent year actually pushes me towards that direction again.
Yeah, Paula, you have your hand up.
Yes, it's something that you just mentioned. I mean, that we expect the GI to have a strong impact in the dust, right? So what the paper by Giovanni Di Piero have shown, right? That trapping is so effective that we will expect them to see, but we don't, or it doesn't seem to be a signature that is common in early disks. So yeah, that's why I don't know how to reconcile these ideas actually.
Yeah, I mean, it's true that there are predictions where the GI makes rings of solids in some sense, if it turns on and off at the right times. I think maybe that was what Giuseppe was heading towards. If I don't want to put words in his mouth, but I see him nodding. Thane, I know you've worked on the idea of a hybrid thing. Why don't you weigh in?
Yeah, so I put hybrid scenario, but I guess I sort of disagree with the premise of the question, which is that there has to be one mechanism. So I'll kind of work from a different standpoint. If you look at the population of directly imaged planet mass things, That includes both things like HR8799, which is a 4-planet system in resonance with atmospheric chemistry that seems to suggest it probably may have formed in a core accretion friendly manner, and 2MeS1207b, which is obviously a binary companion, right? So that did not form by, there's no way that formed by core accretion. And those occupy the same range of semi-major axes, right? So I don't think it has to be one or the other. I mean, the other thing that's sort of, I think is sort of a logical flaw that we fall into, which is that, you say, well, forming a 5 or few Jupiter mass planet at tens of AU is difficult for core accretion. Therefore, it didn't happen. No, it's difficult for core accretion. Therefore, these objects should be rare, which is exactly what we find. So I guess I see what would be would be really interesting, though, is to study the demographics of objects once we have many more new detections. So there's a paper by Caitlin Crowder that I sort of riffed on in one of mine, which tried to plot the mass ratio in semi-major axis for objects that we think formed by core accretion and objects that we think probably formed by fragmentation or disk instability. And their argument is that you can actually start to distinguish between these two populations. And if that kind of holds up in a way, that might be some helpful diagnostic.
Yeah, thanks. Can you put that paper reference in the Slack or something? All right, so Dominique, you have your hand up.
Yeah, so actually, Thane just mentioned Caitlin Crowder, and I was just thinking of Caitlin Crowder's work with these GI unstable disks. And I think she has a few of these simulations that indicate that if you actually have an injection of material from the larger scales, for instance, like these accretion streamers that we're starting to see from the envelope, that can actually help to trigger gravitational instabilities at larger scales in the disk. So I think that's another factor that we have to think about. And especially if we're thinking about the class 0, 1, and class 1 phases, that's not something that we can ignore. We have to take the envelope into account.
Yeah, good point, especially in those early phases. I think since we sort of touched on the next question already, maybe we should just shift to it, Inka.
Yeah. So this is a bit more about the future, and what do we expect? So a few young planets have been found, but upcoming facilities are expected to find many more. Presuming that new ground-based facilities and JWST are sensitive to Saturn mass planets with orbits at tens of AU, what do you think will be the most common discovery? And what is that? Yeah, what do we learn from that? Looks like most people think we're going to find a lot of young Saturns and Jupiters in the narrow disk gaps. So Thane, why don't you start and give your opinion about this?
All right, well, you're not gonna like this answer. I actually chose very few, and there's just a couple of technical reasons for this. So for example, with the James Webb, the nearest star forming regions like Taurus or Upper Scorpius, those are 100, 150 parsecs. The beam size for JWST, for its sort of sweet spot for high contrast imaging, gives an upper limit to the resolution at 15 to 20 AU, so 1 lambda over d. We already know planets in fully formed systems are extremely rare at those separations. And also the beam size for it is such that, if you take the point spread function and convolve like an astrophysical scene between a disk and a planet together, you'll have a lot of blending of that signal. It can be very difficult to separate out those two sources. And so I foresee a lot of candidate detections, but a lot of arguing over whether something is a disk feature in a planet, which is like we've kind of been through before. But I think there is hope, though. And so one of the good things that JWST will be able to do, I think, is give much more conclusive interpretations of wider separation candidates we already know. So 163296 has a candidate companion, 100546 has a candidate companion. The unnamed system, which is obviously AB Auriga, which I present, also has a candidate companion. But the ground is just, the problem with all these systems is that, the processing techniques in order to be able to trigger detection in the first place can be aggressive, and it gets really complicated. You need the stability of space. On the ground, I think what I'm really excited about are the capabilities you might have, like going forward from what MAG-AO has done with H-alpha and what Muse has done. If you combine essentially a higher Stroll version of Muse, that is going to be very powerful, I think, for detecting accreting planets. And if you're able to have a system with a near-infrared wavefront sensing, like you're going to have with Skexio and then with Keck, that takes all these systems that are optically faint and allows you to get good corrections for them. And now we'll be able to, for the first time, be able to get really sharp images of those systems.
Okay,
so
thank you.
I hope, we'll see.
Yeah, sorry, I'm just gonna move on to Andrea, who raised his hand first.
Yeah, I would like to comment on what Tien just said, because we went through this process of understanding what JWST capabilities are, very painful in the last few months. And my one comment is that disks with large rings are very rare. Okay, so it's not that we are talking about that all the disks have planets at 60 AU, right? So we are talking about a fraction that is actually very similar to the fraction of wide separation giant planet, or even less, right? So the question is, so there's a very strong bias here. We're not talking about the large population of disk or planets. The second comment is that, at 4 micron, it's true that you have a disk, but there is not much scattered light you get at 60, 100 AU at 4 micron. So, the disk is not very relevant there, right? So if there is a planet that emits, if you have a young Saturn with a temperature of 1200 Kelvin, it's going to be relatively easy to distinguish this from any disk feature. So,
No,
you disagree?
I would disagree with that. But yeah, I mean, it can't. But one thing it can do, though, is that if you have a population of embedded objects, then maybe the 4 to 5 microns can bring it out. If you do this with ELT, like with METIS, that's gonna be really powerful, because now instead of having a 6.5 meter primary, you have a 39 meter primary, and that is my personal opinion is that is when we'll really start to see these detections take off.
Okay, Julien also raised his hand.
Yes, can you hear me? Yeah, so I'm not as pessimistic as Thane for James Webb, because we simply don't know, what we're gonna get once we go from a few Jupiter masses limits to a fraction of Jupiter masses limits, even if the angular resolution is what it is. And also, I've been playing quite a lot with doing PSF subtraction without coronagraphs. I'm supporting coronography, but I often like to remove the coronograph. And there's an interesting parameter space there. And also using the IFS or IFUs, maybe with the sensitivity, suddenly we're going to find stuff with bracket gamma signature. I don't know if so far it's really difficult. So I don't know. I mean, I'm still optimistic. I don't think it's going to be all over the place. But before we have, well, hopefully it launches on time, and I think we're on track now, but before we have the ELT and the maturity of METIS or things like that, I think, James Webb is going to play a role here.
Okay, so I'm going to start wrapping this up with Christoph. Do you have a short comment?
Yeah, I think my point is that we might be able to use the kinematics to guide direct imaging. And I think at midterm, in the next 3 years, a combination of the two will be very useful. So we could use ALMA to search for non-Keplerian motion and target those signatures to look for via direct imaging with JWST or METIS in the next few years. So there's potentially some discovery space there that might be interesting to explore.
Okay, so with that, I think we're going to move to the next question, which is still closely related. Sean?
Yeah, so this is just building on this conversation about where we're at now tied to the future. And I think, we sort of started this discussion, but I'm curious to hear what people think about why there are still so few planets. So Thane mentioned some technical issues, but I'm sort of curious to see what people think. And I know that Kate has been thinking about this a lot, so we can start the conversation with building on that conversation with Kate.
Sure. So I guess to start, I'd point to a couple of things. One of them is, well, I guess that they all kind of stem from the fact that we're using H-alpha as the primary tracer for finding accreting protoplanets right now. And there are a few problems with that. One of them is you really don't need very much disk material, small grain dust, or even circum-secondary dust to extinct H-alpha. An additional issue is that we have every expectation that accretion processes will be somewhat stochastic. So, if you look if you do your survey of transitional disks and you don't see anything in one epoch, maybe if you return, Connor Robinson and some other people have done some really great work on variability, say in T-Tauri accretion, and it can be sort of up to an order of magnitude. An additional issue that I think we have is that we're operating, we should be clear, we're operating at the very hairy edge of what adaptive optics technology can do, right? In that sort of the first generation, at least, of these high contrast imaging instruments with H-alpha capabilities are achieving Strel ratios that are laughable compared to what we get in the near infrared. And then kind of the last thing that I would just point to is that H-alpha is not even a particularly good accretion tracer for stars, in that it's kind of wound up with activity. And so I think moving towards longer wavelength accretion tracers, even eventually sort of, I think the most powerful accreting object tracer for stars and brown dwarfs has been near ultraviolet emission. So that's obviously in the very far future, but I think we have yet to understand. I think there are already a number of things we can point to explain why we haven't seen more H-alpha accreting protoplanets. It's not that surprising or hard to come up with a number of explanations.
Thanks. Yeah, I do wonder. Do we feel like we have a good idea of what kind of accretion luminosity to expect in this scenario? Do we know how planets accrete? Like, is it really magnetospheric accretion, like in a T-Tauri?
Yuhiko Aoyama and Christophe Morosini's group, Gabriel Marleau and some others have done some really great work, and the Tonativity papers, like a ton of work on planetary accretion models. And I think the magnetospheric accretion paradigm probably breaks down at lower masses. We don't know that protoplanets and even accreting brown dwarfs have strong magnetic fields. My understanding of Yuhiko's models, for example, is that we expect actually the physics of the emission to be very different, because we expect most of, for example, the hydrogen lines to come from the post-shock region in the photosphere of the object, and not necessarily from the infalling or pre-shock region. And that's a very different sort of physics. So one of the things I'm really excited about with James Webb is that I think if you can resolve a number of accretion tracers and do line ratios, that's a powerful way of distinguishing between sort of which of these paradigms you're operating under.
Yeah, that's a really interesting point. We'll go to Andrea, and then we'll move on to the next question, which is somewhat related. Go ahead.
I want to make a comment about also, Kate talked about accretion signature, but there is also just thermal emission. And, if you look at the contrast curve that people have achieved also with Keck, for example, the sensitivity, the current sensitivity, there is a lot of uncertainty depending on temperature of the planet, but the correct sensitivity is between 1 and 5 Jupiter masses or higher, right? And so if you look at the masses of planets we estimate from the gaps, you get Neptune, Saturn masses, right? So it's clearly below. So the only planets that could be within the reach is PDS 70, and we found them. So, there is clearly a point that in terms of thermal emission, the observation are not sensitive enough to get most of the planet we derive from gaps.
Yeah, I agree, and so do the poll takers. So, Nika, let's move on to the next question, please.
Yeah, so next question is indeed somewhat related to these, like the signatures that we're looking for, the kind of the different types of techniques and instruments and wavelengths. But also, so what is it that we're actually trying to learn? If we do detect signatures of young planets, what will we learn from them? And yeah, something went wrong with the previous poll, but you should be able to select more than one option now. So yeah, well, the results are coming in. It goes up pretty equally, which is probably because we have more than one option. Julien, do you want to comment on these findings?
Yeah, I'm really glad we could select more than one option because I wasn't sure at all what to say. It depends a lot on how we detect those planets. So obviously for accretion rates, you need some kind of emission line, some kind of tracer for accretion. And so that's the case for H-alpha, but maybe also for the lines that Kate just mentioned in the chat. If we can do direct imaging and the systems are, and the separation, the actual physical separation is not that big, then why not do orbital filling and dynamical masses independent from the models? And obviously with James Webb and the wide range of wavelengths for characterization, we can do the photosphere properties and the other, atmospheric studies. And then obviously that's less my specialty, obviously, but planet disk interaction, and finally understand, like what causes all these structures that we see in disks. I mean, definitely there's a little bit of everything, but I don't know how to, which one's going to prevail.
All right. Richard raised his hand.
Yeah, so I'd really like to build on that point about the planet disk interactions. I think if we're detecting embedded planets, then we're going to learn a tremendous amount by studying how the disk is reacting to those embedded planets. And in particular, if we're able to trace the velocity structures around these planets and the density structures and temperature structures, we're just going to learn a fantastic amount about what that planet is doing. And I think really that the better handle we have on the disk structure itself, the more information we're going to be able to learn about these planets when we finally detect them. And that's really sort of the powerful thing about detecting planets through their CPDs or their kinematic features, is you get that disk information for free with those sort of observations. So I think there's a huge parameter space that we can start to explore with those sort of observations.
Thing?
Yeah, sorry. No, I was just going to say, I think it'll be really interesting to see, the challenges with interpreting the SEDs of some of these objects, right? Because you can get multi-wavelength photometry or spectrum, but it's unclear, just from that, it's unclear, I think, whether or not you're getting emission from a circumplanetary disk or from thermal emission from a newly unveiled atmosphere. And that way, the temperatures are can be fairly similar between those two if you compare the models for circumplanetary disk emission to the models for, like the youngest substellar objects. And so that may be a bit, so you can get a temperature and a luminosity, but interpreting what exactly that means may be an interesting challenge.
Yeah, we don't have many raised hands right now. I don't know if Kate has anything to add to this.
Sorry, I was posting in the chat, but
No worries.
in terms of what do we think we'll learn from multiple planets, or from finding accreting planets other than their accretion rates? There is one other thing that I can think of, which is just that I think if we could robustly get their accretion rates, which may be tricky, I think this could be one path towards understanding their formation mechanisms or validating formation mechanisms, in the sense that, for example, if you look in object mass accretion rate space at where the substellar companions lie, they're sort of strangely high. And that could be for a bunch of reasons, because we're only seeing the upper envelope, the sort of strongest accretors, because we have no idea what the accretion paradigm is, and we're completely misinterpreting the signatures by assuming that we can extrapolate from T-Tauri stars all the way down into the planetary mass regime. Or if they're truly high, though, you do expect, there was a nice paper by Stamatelos and Hertzig sort of predicting what you expect for accretion rates as a function of mass in the sort of, these objects formed via gravitational instability in a disk, and you kind of expect a flatter relation with mass that could be consistent with what we're seeing, but with all the caveats that I just said. But I do think that if we could calibrate the accretion tracers, we could probably inform planet formation mechanisms as well.
Okay, thank you. Yeah, so we think we're gonna wrap up this whole discussion about planets now and move to another topic of this conference, which is dust. So Sean, go ahead.
Yeah, enough about planets now. Let's move on to the disks themselves. I'm quite curious to see what people's answers to this question is, because I think in my career, I have been pretty firmly in each of these camps for some amount of time. So I'd be interested to see what people think, where most of the mass and the solids are in disks. And then I'm going to have, since we had this great talk by Akamasa on dust earlier in the conference, I'm going to actually start the conversation with him. Oh, he has his hand raised too. Yes, we'll start with Akamasa.
Yeah, thanks.
What do you think, actually?
It's okay. Let's first say the poll, and the result is kind of diverse. But the top is planetesimals and primordials, and I polled as the same, and probably it reflects our wish, right? So we wish that we are looking at the building blocks from the protoplanetary disks, and otherwise it's kind of discouraging. But also we have to be kind of open-minded, because, for example, polarization was not due to magnetic fields, or scattering is important, but of course we wish it to be much simpler. So probably because the solids that we are observing as a dust in class 2 disks have less massive than the exoplanet core masses. So probably they are already gone or in the form of planetesimals. And well, I think one important thing is that the migration timescales, because if you have pebbles, they radially drift very fast. So that's why we have a lot of substructures to keep them. And also, even if you make planets in the very early stages, you need to keep them towards like a few mega years. That's very hard task. In that sense, planetesimals are very nice, because if once you form planetesimals, they can survive, I guess, at least in terms of the migration timescales. So we can have planetesimals as a mass reservoirs, and that's my personal view. And also concerning the 100 micron size dust, which is, I know, controversial, but what it is telling us is that we are able to see millimeter and centimeter grains, but if there's absence of them, then that tells us a lot, right? So if the grains stops growing, at that size, then we know the physics governing them, so that we can learn the building blocks of planetesimals or planets. Yeah. So, is there anyone who wants to add more?
I actually want to ask Jane what her thoughts are.
Oh, I was not expecting to be asked this question. So the answer I picked was in planetesimals, and otherwise primordial, but I don't really have a good justification for this. I was going to say in planetesimals simply based on the fact that, you know, the masses of class 2 disks would imply a very high conversion rate to planets and planetesimals if this was the starting material. This constituted, you know, pebbles and small dust. But I do think the idea of some of the dust we're seeing being debris is kind of interesting. You know, if we do have planets and planetesimals, it stands to reason that we are seeing debris. It makes sense from what we know about debris disks.
Yeah, that's very interesting. I like the debris idea too. It's sort of come up repeatedly. I know Scott Kenyon is a big fan of the idea. Pat Sheehan.
Yeah, thanks. I agree with everything I think that's been said, but I just wanted to highlight too the evolutionary aspect of this. You know, you would hope at some point, if you go early enough, you would see presumably more, you know, to a point before planetesimals have formed, you would see more mass in the dust. But I guess there's sort of a question of when is that, and do we see that, or do planetesimals form right away? You know, class 0 disk masses are certainly higher, but are they enough? I don't know. Or are there still planetesimals then? And I think that's kind of an interesting question. I don't know if I have a good answer, but I thought I'd at least put that out there.
Yeah, Giuseppe.
Just a curiosity, I voted for planetesimal primordial, but isn't it strange that almost everyone, based on the previous questions, believed that planets form before the class 2, but now almost no one thinks that the solids are in planets?
Well, yeah, that was, I will say that it was kind of deliberate because I was quite curious to see how internally consistent we are or not, including the next question, which sort of weighs in on it as well. I agree. It's hard to be internally self-consistent because I think we don't have measurements that sort of.
That's a chicken and egg, right?
Yeah, exactly. Okay, let's do a couple more before we move on to the next one. So Leslie has his hand up.
I just want to kind of echo the same statement that Giuseppe just said. In fact, this is my concern. Just like Sean, it seems like every paper I seem to get a different answer. I wanted to pick multiple answers, big and small, because the polarization from scattering clearly has some problems with the large dust grains. And so it seems like this is an evolving question that we still don't have a very firm handle on. It's very surprising we have jumped between different answers there.
So I think let's actually, just in this context, move on to the next question, where I fully expect you all to be, again, internally inconsistent. But let's see what people vote.
Yeah, so the next question is indeed, well, this is more related to the dust masses that we're estimating. We typically adopt a solid mass opacity coefficient of about 2 at 1 millimeter wavelength when interpreting observations. But in a disk average sense, for the purpose of estimating the total mass, how terrible of an assumption is that? We can go from either very overestimating to very underestimating.
This absorption opacity or total extinction?
Sorry, I did not get that question.
Well, my question was, is it the absorption opacity or the total one, the extinction?
Absorption.
It's absorption, right? Yeah.
Okay, thank you.
Okay, so Okay, well, it's about right. It seems to be very popular. We're not doing too badly. Maybe everyone just goes for the golden average here. Carlos, would you like to start the discussion here?
Yeah, so it's funny actually because I was just discussing this with Aníbal Sierra a couple of weeks ago, and we made some calculations actually, and I can share you some plots in Slack. So what we did was to simulate thousands of disks with different densities and with different density profiles and different luminosities for the central star and different particle size distributions. And we assume a dust opacity for absorption. We assume that this is optically thin, and it's not surprising. We underestimate always we always underestimate the mass. But what we see is that we underestimate more the mass if we go to a more massive disk. And I think this is important. When the disk becomes optically thicker, we underestimate more. And the factor is for 10 to the minus 4 solar masses disk, we recover 75% of the mass. But for 10 to the minus 3 solar masses, which is more or less what we expect, we only recover 25% of the mass. So, and I think these disks were smooth, and I think that this is going to be worse with substructures, because substructures probably are very optically thick, so you are hiding a lot of dust mass here. So I don't know if you have any other comment.
Yeah, well, so I have maybe just an additional point here. That is, I mean, it's true that in all these substructures, dust is much more concentrated, but the same is actually true for all these compact disks, where all the dust has likely drifted inwards. You would have huge concentration as well, and the dust is optically thick in the inner part. So what are thoughts about that? How much are we underestimating there? And are these like two different problems? Andrea raised his hand.
Yeah, I don't have an answer to your question, but I want to make another comment, which is, no, yes, we are definitely underestimating mass because there are optically thick regions, but I also wonder how much mass we are underestimating because solids are locked already in a meter-size object or larger, right? So, I don't know if Carlos, when in your exercise you always assume kind of collisional cascade profiles, but I think numerical simulation, and I don't see Till in this panel, but maybe Paula can comment. When you do grain grow, it's not that you really have a simple collisional cascade. You can have a bimodality where you have a lot of large objects that will be completely invisible by our observation. So how much mass are we hiding in boulders of planetesimals already?
Yeah, I can comment on that.
Yeah,
because,
go ahead.
In one of our recent works, we actually, the one that Ilaria cited, we have included kind of what we call weak and strong traps, and see how that fits in the this mass or task mass stellar relation. And the problem there is that we notice that in some cases we have boulder formation, and then we will create a steepness just because of that, because a lot of the dust is in bigger objects. So not because of the drift, because we are stopping the drift anyway. So it was a hard problem to explain actually the relation that we have for these that are transitional disks or substructures, because that relation is more flat. But in none case, I mean, there was no case that we could produce it, because if we have traps, we form boulders, and then that relation should go steep. So I don't know the answer to that.
Okay, so I'm afraid we're gonna move on. Also, nobody has their hand raised, to more exotic topics with hopefully even more controversy. So, Sean, please go ahead.
Well, all right. I would say that magnetic fields shouldn't be an exotic topic because basically everyone assumes that they're important in disks. But we're sort of trying to get at here what people think would be the prospects for actually figuring this out, either theoretically or observationally. What would be the way to get some evidence to learn about magnetic fields? All right, so fine. The question answers are all sort of observational, but that's just my own bias. We should talk about the theoretical side as well if we think that there's a distinguishing characteristic there. But so far, not much success in learning about these things. But obviously, this is important enough that we should invest a lot of effort here. So I'm, you know.
It looks like people are honest.
Yeah, I guess people are afraid to think of magnetic fields. I'm gonna first toss this to Ian Stevens, just for his thoughts on the observational side, and then we'll maybe talk to some of the theorists as well. Ian, go ahead.
Thanks, Sean. This is one of the main things I've been trying to do for a long time in disk, and I feel like I'm starting to exhaust observationally with polarization which one of these might work. But that being said, there's still avenues I think observationally with polarization we still can do it. Of course, it says, quantitative constraint. I think in morphological constraints already hard enough. And so that's going to try to be doing both the spectral line polarization. That seems like it's very hard to do because the lines are thermalized for the most part because there's high densities in these disks. And so if you go for some lines with higher dipole moments, those are a lot less bright and you're already pretty sensitivity limited. And it looks like you might need to be going to 20 AU resolution maybe to see signals. I think doing like the GK effect, that's going to be very tough. As far as doing continuum polarization, there has been some evidence, some tentative evidence of saying, okay, well, this definitely ain't just based off how spectral or the polarization is changing with wavelength. It does look like some things look like alignment, but I don't know if we can definitely say it's alignment with magnetic fields. And I know Haifeng Yang is working on a study that's saying, well, it might, with how much gas there are in the disk and with how much larger disk grains are compared to the ISM, it might be almost impossible to align grains with the magnetic field within a disk. So that can make things tough. But those two methods don't even give you, at least not directly, a measurement of the magnetic field strength. So the other big avenue, of course, is to look at CN or do Zeeman effect. And our first tries of doing that have so far not worked, but we're, or I should say, we have not detected any definitive Zeeman effect. But that being said, we're getting constraints around 5 to 8 milligauss for the upper limits, and it might not be, the field strength might not be that long. I think one avenue, at least the way I voted for this one, is still spectral line polarization, specifically trying to do Zeeman effect, but it might be something that requires us to do something like 24 hours of observations in CN in order to get some really, really faint signals.
Daunting, but to be clear, I don't just mean field strengths. You can quantify morphologies too. That's fine.
For sure.
But let's see, Meryl has her hand up.
Yeah, so I think this is more going to be a question to people who know a lot more about this than I do. But I was wondering, so for example, in disk formation theory, it depends a lot on whether you have a magnetic field and what kind of effects you take into account, what size of a disk you can form. So I was wondering if we would have large surveys of multiple regions of young disks at different stages, would those, and measurements of disk size, would those results tell us something about, well, maybe the strength or anything else of the magnetic fields? Would that be relevant?
I don't know the answer to that. Let's see. Jake.
Yeah, I'm not sure if I have an answer to that. I mean, since I was tagged on this to discuss this topic, I thought a little bit about it, and I'm still not sure if I have a favorite method, to be honest. I sort of want to do them all, right? But I guess if I had to pick, it would either be the spectral line polarization, specifically the hyperfine stuff like CN. Although again, I echo what even Ian says, that my understanding is that that's pretty difficult to get more than an upper limit right now. But I actually chose the best bet is to look for indirect traces of winds. And the reason I did that is simply because there's sort of two ways to do a wind in my understanding. It's photoevaporation or magnetic fields. And I feel like the least number of complicating effects, the better, right? And so looking at turbulence in disks, well, there's a whole bunch of different things can produce turbulence. And so how do you distinguish between like VSI and the MHD and that sort of thing? But winds, I feel like there's like I said, there's only two ways to go with that. And if you can find a key sort of thing, like perhaps the inclination of the outflow can tell you something about whether it's magnetic fields or photoevaporation. All of these are hard, but that's the one I would pick.
Yeah, that's an interesting point. In the interest of time, we're going to move. I'm sorry, Mario, I see your hand, but we have two more questions to do in the next 8 minutes. So I want to pivot again and pass it back to Ninka. Blame planets. We took too long on planets.
Well, but we like planets. So next question, we're moving more towards the topic from yesterday, environment and multiplicity. So there's still a lot of work to be done on asserting how the immediate external environment can affect disk properties and the prospects for planet formation. Which environmental factor is most pressing in these regards? Well, the votes are coming in. Maybe, yeah. Jane, would you like to give a first impression?
Right. Well, so I voted for binary companions just because that's the one where we actually know that they are common, but also this is the only phenomenon for which people have done dedicated studies. So in some sense, this is not a very fair question. It certainly does seem for the other three phenomena that they are occurring more frequently than people had thought in the past. And for that reason, they warrant additional study.
Yeah. Nicolas, do you have anything to add to that? Being the review speaker on this topic.
Yeah, I'm happy that binaries are getting attention. As I said yesterday, I think multiplicity also plays a role at the very beginning, and then we are sometimes seeing single stars that were once part of multiple, so that should leave some signature. And that also provides a way to, I would like to answer all of them actually, but that also provides a source of free-floating stars like flybys. But also there is the envelope accretion, actually, it's also very important. It has been shown that, for example, the infall coupled to magnetic fields can also create prominent structure. And we're seeing, for example, AB Origa that seems to be accreting from the environment. And that creates structure that we might think are binaries, but perhaps are not in the outer parts. And lastly, I think one aspect that we should consider also is the radiation field where the stars are located, because sometimes you can photoevaporate from outside in the disk. So that's, but I'm happy with binaries actually.
Dominique has her hand raised.
So I know you say envelope accretion for the class 2 phase, but obviously for the class 0-1 phase, that's going to be something super interesting to study. And we are seeing more and more instances where we do have these large scale streamers feeding directly from envelope to disk, including towards sources that have really tight binary structures in the class 0 phase. So it'd be interesting to try to find more of these streamers and see if they're connected to some sort of binary structures.
Giuseppe?
Yeah, I was just going to say, why just binaries? Triples and quadruples are all very interesting. And we have a number of examples of triple systems that are very interesting and show that the structure can be quite affected by that.
Yeah. I don't know, is there anyone who hasn't spoken yet? Yeah, go ahead.
There was an interesting comment on the Slack by Michael Kaufman saying more on a large scale, it would also help to get a constraint on magnetic field strength in the entire star forming region. So perhaps by coupling different mechanisms, we can kind of measure which one is dominant, and we can actually have indirect measurement of the strength of the magnetic field, for example.
Interesting. So that kind of ties back to the previous question. Yeah, well, if nobody else has a comment at this point, I think we can move on to the final poll, and we may actually make it in time. Sean? Yeah, so this is just sort of harping on the binaries or multiples, I guess. And binaries is a slip up. It should just be multiples. But I am sort of curious, right? We know that binaries or multiples are really important for exoplanets and for disks. And it seems like, at the top level, there's been some really nice work with ALMA for this, but not as much as you'd think, given how important they are. So I think we're sort of nudging people to think a little bit more about the role of a companion star in the planet formation process. And I think we'll start this off with Ian Chekala. And no, I'm not like intentionally passing all these comments to my former PhD students. It just seems that way. I didn't organize these in order, I promise. But Ian actually, before we even start the conversation, wanted to clarify the question, I guess. So go ahead.
Right. Yeah, I think it's been sort of a common theme in discussing a lot of these questions is that the devil's in the details. And I think that's actually where a lot of the interesting work is in discussion. And I think this is one particular area where nomenclature has a very strong implication for the dynamical effects that are there. And it really matters whether we're talking about circumstellar disks or planets that have a external binary companion, which is also called S-type. I always find this nomenclature super confusing, but that is this type of system studied in Moen Crater, or are we talking about circumbinary disks and or planets? Obviously, the dynamical situation is going to be more complicated than a single star, but I think they're just very different systems. And so even in the same question, we have sort of two different dynamical effects. One is the disk is truncated and planets form further out. I think that's probably referring to the circumbinary case. And we actually do have very few planetary detections. Most of the detections in that category come from Kepler. And at least from that sample and some of the direct imaging work, I'd say it's not necessarily clear that the circumbinary planet occurrence rate is less than that around single stars. I think it's entirely consistent, but uncertain. For the single star case, yeah, certainly. I think also this is a case where as we learn from the direct imaging world, until you have an orbit, a projected separation doesn't tell you much about the relative geometry of the two systems. And there are very few systems that we actually do even have a partial orbit. And I think Nico Coelho nicely highlighted the sort of deep amount of dynamical and simulation work that is required to actually make definitive statements about particular binary systems. And I think just all of the great work around the HD 100453 system just demonstrates how much context is really needed to sort of make a definitive statement about this. So I guess my contribution to this discussion is really just to say that the observations needed are actually deep and detailed if you want to actually make much more statements with sort of beyond broad trends. I certainly think the exoplanet surveys and the flux surveys as a function of projected separation absolutely support the idea that planet formation is suppressed in S-type binaries as you get closer. But I think the sort of detailed study is deep dives on particular objects where we know the geometries.
Yeah, the orbits is probably what stops us from getting more ALMA data, I suspect. There's always that ambiguity. Giuseppe.
Yeah, I'm a bit puzzled by the answer that got the most votes, because I mean, we don't really know what are the physical processes in the disk that are required for planet formation. So how can we know that the torques disrupt them? And how deep into the disk can the torque really affect these kind of processes. I mean, they certainly die out if we move much closer in. So I was a bit curious about this. Exactly what do people think about how can the torques from a binary disrupt the physical processes?
Maybe I'd pass this on to Nico Coelho to see.
Yeah, I just wanted to say that perhaps we need to make a difference between like S-type disks and P-type disks. I think Giuseppe's concern is about P-type disks at the very edge of the cavity, the inner cavity. So in that case, yes, of course, you can form planets farther out. And it has also been shown that once you form planets, they tend to migrate and sometimes they lock in some orbital resonance that allow them to move farther down, which saves the planet in a way. Regarding S-type disks in binaries, I think there's a more dramatic effects because you have the outer guy shaking the disk every single time, and that might have an effect on the relative velocity at which solids encounter. So the onset of planet formation might be a bit more tricky, but again, we don't know really the details of planet formation, so it's hard to tell. But I would differentiate this kind of two disks because they live very differently, in my opinion.
Yeah, that's a good point. So we're at the time limit. I see Jeff still has his hand up. Why don't we finish with your comment?
Thank you. Yeah, I agreed with Nico about distinguishing both types of planets, but I mostly wanted to comment on what Giuseppe said. I agree absolutely with him. And I was surprised that nobody thought of spiral arms as a way to concentrate dust and to promote planet formation. And as an advertisement for work by Hossam Ali, he also showed that when you have a binary inclined with respect to the disk, you have a different precession speed of gas and dust, which can create traffic jams and could lead to inclined planet formation. So that could also be a favorable environment to form planets instead of destructive.
Yeah, it's a good point. Let's see, am I frozen? Okay, we're going to wrap up because we've hit the hour. Thanks very much for, I mean, this is great. I wish I could gather you people every couple of weeks to propagate my own ideas and interests, but I won't burden you with that. But I thought this was a lot of fun, and I'm glad to see everyone participate. Let's, I guess, throw it back to Alvaro and Enrique.
Yes, thank you very much, Sean, Ninke. We're sorry we have to wrap up. This was really interesting. But I see Slack is on fire now, so please feel free to move to Slack to continue discussing all these interesting topics. Before I handle over to John, we want to thank all the invited speakers for their awesome talks, the chairs of the sessions, the moderators and the panelists in the discussions, and all the participants for the great engagement we've seen both on Slack and Slido and all the time. Keep an eye on your email. We'll be sending an email in a couple of days. And that's all. Thank you very much. And I think I'm going to handle over to John Carpenter now for the closing remarks of the conference.
All right. Thank you, Alvaro. Let me share my screen. Where's the play? Okay. I assume you can see my slides.
Yes.
Okay. So I've been asked to say a few words in closing. And I'll try to keep this relatively brief since this has been a great conference, but I'm sure that everybody is a little bit exhausted of Zoom. I think it's not possible for me to do justice to give a summary of the conference. There's just too much. There's just so much wonderful material. So I'm going to approach it from a slightly different viewpoint, and I want to actually go back to little bit of history. So ALMA, when they were doing the construction, they were coming up with the level 1 science requirements and developing what is the main science goals and how to justify the number, how many antennas do we need, what baselines we need, what receiver bands we need, and so forth. And this was culminated in a document. It was the principal signatures were Al Wooten and Tom Wilson, but there's many other people who contributed to the science case. Avin Benjic, Brian Butler, Stefan Guillotot and others were all part of this. And one of the main science goals was was on circumstellar disks. And so this is one of the main science goals. And this is what they actually wrote about what they wanted to do as a summary of what they want to do for a circumstellar disk. That is the ability to image the gas kinematics in protostars and protoplanetary disk around young sun-like stars, enabling one to study the physical, chemical, and magnetic field structures and to detect the tidal gaps created by planets undergoing formation in the disks. So what's great about this quote, it basically hits, is a wonderful summary of what this conference was all about. I mean, we talked about the physical, the chemical, and magnetic field structures, and we talked about gaps forming the disks. So it really shows the how well ALMA, one, their foresight in figuring out what ALMA was going to do for circumstellar disks, and it also, I think, this illustrates the tremendous progress that's been made in ALMA in studying the properties of the disk and aiming toward the main science goals. And this document is about the 15th anniversary of this document is it will be 15 years as of this Christmas Day. Why they prepared this or finalized this on Christmas Day, I do not know, but it will be 15 years coming up in just a couple of weeks. So another anniversary associated with this time. Okay, and like I said, we really touch upon all aspects of this, and obviously the physical structure, getting the very high resolution images of images of disks. I have no superlatives to add what's been said already about the HL tau image, and it's really sparked many other studies and many other basic demographic studies looking how these disk structures, how they vary with stellar age, how do they vary with stellar mass, the disk size, the environment, multiplicity, and all these different aspects. And this is work that's still ongoing. I think we're just starting to really to decipher all of this information that we have gathered. But it's so I think this really started with HL tau is really starting the push toward getting the high angular resolution and understanding the origin of these substructures. It's interesting, we compare the poll with a poll that was done about 4 years ago. There was another disk conference in Chile 4 years ago, and David Wildner, for his summary talk, he polled the audience to see what they thought was causing the rings and gaps in HL tau, and repeated this question for this conference. And it's pretty much the same. I'm certainly, most people think that there's multiple causes, with perhaps planets being the primary one. But so the thinking has largely been the same. Perhaps planets is becoming more in vogue as people study more. But looks like the thinking is very similar. I think the kinematic work that's been ongoing has been very fascinating, looking for distortions in the velocity fields, either localized kinks that associated with planets, maybe more of these flows that may be associated with the flows within the disk, maybe indicating the pressure gradients. And there's other kinks that have been associated with the velocity field that may be perhaps associated with the spiral arm. So this work, Christoph gave a very nice overview talk on that. I also encourage you to see listen to the talks by Richard and Teresa, and Simone and Sebastian have done very nice work at this as well. So I think this is very nice work and really pointing toward possibly that it is actually embedded planets that is causing a lot of these structures that we're seeing within circumstellar disks. The chemical structure, another one of the highlights of one of the main science level, one of his main goals of level 1 for ALMA. I think we're just starting now to see some of the impressive results. Anna gave a nice overview of that, and the ALMA DOT survey, those first papers are out, and I think I expect soon you'll start seeing the papers from MAPS and FAUST. This is some of the data from the I believe it's the MAPS program, showing the different molecules in the 3 of the disks that they looked at, just showing the wonderful different chemical structures and excitations that one can expect when we actually start mapping, getting relatively deep maps in these molecules, and understanding the implication for this for the planet formation will be very interesting going forward. The magnetic structure, Mother Nature has thrown us a curveball on this with the as we just talked about, and we also heard in the talk earlier this week by Akimasa, where the high alpha depths and in many of these disks, the scattering may be the dominant component. So it's going to be a little bit more harder to tease out the magnetic field structure in this, and we may have to rely on the more the Zeeman polarization. But the polarization maps that we're getting out is just amazing, and they're probing the disk structures and the grain size distribution in other ways that perhaps weren't anticipated initially, but are very interesting in their own right. This is another comparison between this conference and the conference from 2016, just showing the word cloud of the different of the abstracts for the 2 conferences. Obviously, there's don't take this too seriously, but I think the words that are perhaps the new words that are appearing, rings and gaps, are appearing more common, and perhaps dust, especially with multi-wavelength dust observations, is appearing from, and the formation, perhaps from the theoretical studies trying to understand the formation of the rings and gaps. But but obviously many similar characteristics as the conference. And I think this just shows that we're making progress on all fronts, but I think the rings and gaps in particular are becoming are obviously, for obvious reasons, are very interesting to study. So what's next? Well, obviously, we've heard a lot about the work in progress, and we've heard through discussion sessions about the future observations of what we like to make in the future. I'll just make this one point, and this point has been raised a few times in the conference about the need for deep observations. And in fact, we look at the original science goals that was written, 15 years ago. They were sort of envisioning, observations on source, on the order of 10, 20 or more hours in order to really probe the kinematics and the chemistry within disks. And what this plot here shows the for cycle 7, it shows requested on-source integration time for all the proposals in category 4, which is mainly circumstellar disks proposals. And you can see that the vast majority of observations are requesting only a couple minutes on source, and only a few are requesting even more than an hour. If I zoom in, change the scale and change the bin size, you can see there are a few proposals that are requesting observations, more than a few hours, but it's relatively a handful. And I think this is where going forward, so I think the main point of this, showing this, is that we're just scratching the surface on what ALMA can really do. We're only integrating typically for a few minutes. And I think as we get more of these very deep integration observations, especially in the spectral lines, for many tens of hours, I'm very anxious to see what that's going to reveal about the kinematics and the chemical composition of the disks. And so I fully expect that we'll start seeing more of these observations in the future. And I'm looking forward to what they're going to show. I think that's going to be very interesting going forward. So a few fun numbers for the conference. We've had, I think this format of having the Zoom talks with the Slido questions and the Slack and the Twitter, I thought it worked very well coming together. It allowed many more participants than normally you get at these conferences. So nearly 600 participants, nearly 200 presentations, and well over several thousand YouTube views and Slack channels, and hundreds of tweets. And as many as at one point we had as many as 365 maximum simultaneous viewers. So it's very dynamic conference, and so I thought really really showed the potential for these type of conferences. And of course, there was the artistic side. So there's 11 poems on the NHL Tau, which you can look at in the Slack channels. And of course, we saw the different illustrations of disks using either donut or artistic work. But I have to say, my favorite representation was the HL Tau pumpkin by Elizabeth Tang. She carved for Halloween this year. I thought, and I shared with many other people when I first saw the image, I thought this was the HL Tau image, but it's actually a carved pumpkin. So I thought that was so kudos to Elizabeth. It was fantastic. So let me just wrap up, and first of all, let me thank a few people. First of all, like to thank the sponsors, the ESO, the North American ALMA Science Center, and GVL and ALMA supporting the conference. They've been very generous. All the ARCs, even also the East Asian ARC, they're very generous in supporting these type of conferences, and so we're always grateful for the support. And they provided logistical support for this remote conference. I would like to thank the organizing committee. In particular, the scientific organizing committee did a wonderful job of selecting the speakers and having a very rich program for us. And the local organizing committee really did the bulk of the work in putting the conference together and making all the different the social media and electronic platforms work. So let me first of all let's all thank the scientific organizing committee and the local organizing committee. But as in many of you know, if you've been serving on these part of these conferences, there's always comes down to just a few individual people who really do the bulk of the work and really make it successful and make it happen. And this was no exception in this case. So I would really like to thank Alvaro, Enrique, and Antonio for really putting this together. They're all the co-chairs of the local organizing committee and the co-chairs on the scientific organizing committee. And Alvaro and Enrique, they really did a marvelous job of pulling this off and answering questions and making the organization work. So I think we really owe them a tremendous amount of gratitude and tremendous amount of applause. So thank you very much for Alvaro, Enrique, and Antonio for all your work to make this so successful. So. Okay, and then my last slide, I would just like to thank all of you for participating. Alvaro and Enrique have already said it. We had such a wonderful group of speakers, the panelists, the discussion. We had such lively discussions, and they're very well prepared for discussions, and all the contributions to the contributed talks, the invited talks, and the Slack discussions. I thought really made this this conference fantastic, and it really shows the potential for these type of conferences. So I would like to just thank everybody for their participation, and hopefully we can actually continue some of the discussions on the Slack over the next couple of weeks as we go and continue to review the talks. So with that, I guess I would like to close the conference, unless Enrique or Alvaro, is there any final remarks or questions that are coming in?
No, thanks John for the closing remarks, and as you said, thanks to everyone. Thanks Alvaro, thanks Antonio, thanks to the LOC, the SOC, speakers, moderators, chairs, and contributor speakers, poster presenters, everyone.
Yeah, I just want to say I've been checking. I think there's going to be a total solar eclipse, and I don't know if it's North America or Mexico in 2024 and another one in Spain in 2026. So maybe we should organize something like a 9 years after HLTAO or 11 years after HLTAO conference. Just some ideas. Thank you, everyone.
All right. Thanks, everyone.
Thanks.